That's the clap for cutting later. Hello, welcome to the August 2021 meeting of the Forth 2020 Facebook group. I'm happy that we have lots of people joining us, and we have interesting talks about Forth, of course. And our first speaker will be John Hardy. And he's talking about a Forth threading strategy on the Z80 or Z80. Let me know what the right pronunciation is. I know this is probably a British US thing. Okay.
It's Z80. It's Z80.
Right. Right. Okay. Yeah, please go ahead.
Okay. Thanks. Thanks, Ulrich. Yeah. I'll just share my screen. Hopefully this works. And can everyone see the screen? Yep, cool. All right. Okay, so I thought I'd just introduce myself. I've been involved in with the Z80 for 40 odd years. Since the late 70s, in fact. In 1983, my friend Ken Stone and I published a computer kit called the Tech One, which was based on the Z80, and it was a popular kit in Australia. So quite a few people built it and got their first experience of programming microprocessors and that sort of thing using this one. In fact, it was many people's first computers that told me that since that. And we started a Facebook group about 2 years ago. I've been sort of coming back to the Z80 a little bit because I've since then had a career as a software engineer. And in that same period, in the 80s, I first became acquainted with Forth. I read Leo Brody's book and generally admired it, but didn't have working versions of Forth until more recently. When I was starting to look at projects to do with my Z80 in relationship to the Tech One Z80 group on Facebook, I started to think about Forth again, and because the main problem with the Tech One was it was a great electronics kit, but it wasn't a terribly good environment to program because it was a simple hex pad type arrangement. So since then, I've been working with group members, and we've basically got a serial interface happening for the original board, and of course we've got successor boards also being made. This is the point. This kit is still being made, nearly 40 years later. So, of course, you don't want to do basic. Some people already have done basic. We don't want to just repeat the whole, that cycle. I thought Forth is a much more interesting language to do because it fits into the assembly language mindset. If you've been programming a Z80 in machine code, programming in Forth is actually a breath of fresh air. But it's still got that something about it that I really love about assembly language, and I also love about Forth. So there's just something about the aesthetic of Forth that I particularly like, and it actually makes assembly language programming so much simpler if you start using Forth techniques. So I've been working on Forths in various forms over the last 2 to 3 years. I just went into it boots and all, not really knowing how to make the fastest Forth for a Z80. This is by no means the first Forth for the Z80. There are many. So I've been studying all of them, in particular Camel Forth, eForth, and various other implementations of Forth for the Z80. So the questions are, why am I even doing this? Well, because it's retro computing. You don't ask why. It's the art of it. It's the enjoyment. It's the limitations. It's all of these things are part of it. But nevertheless, we're still interested in performance and efficiency. In fact, you know, these are very interesting challenges in the 8-bit world. So, and that said, you know, the Z80 is probably a little bit under spec for Forth. Forth is better on a 16-bit processor as a minimum, but, you know, getting things working on 8-bit is still a lot of fun. So as I say, the main thing is, are there any improvements that can happen? This is a very well-trodden path. The Z80 is one of the original chips that people implemented, the first widespread Forths. So the questions I have are whether there's anything left in the tank. Just to remind people, because I know a lot of people started on the Z80, but they might not have thought about it very much in more recent years. This is the general layout. We basically have 3 sets of, we've got 3 register pairs that are most used for Forth. That's BC, DE, and HL. We also have an alternative set, but they're kind of a little bit hard to get access to efficiently. So they tend not to be so easily used. They're more a good idea on the drawing board than an actually very useful feature of the Z80. That goes for the index registers IX and IY as well. They're somewhat more useful, but they're kind of slow compared to the normal register pairs. So a couple of things when I started implementing my first Forth was to follow some of the advice that I saw, which was to keep the top of stack in a register. And this is an obvious optimization because so many operations just work on the top of the stack, and therefore it's a worthwhile optimization. I did look into also the idea of using the second to the top of stack as well, but that didn't really work out. So essentially, you know, that's a worthwhile thing to do. So I set, in my particular Forth, I'm using DE as the top of stack. The other interesting thing about Forth when implementing on an 8-bit microprocessor is that it's 2-stack architecture. This is problematic because Z80 only has 1 stack, unlike say the 6809. The single stack architecture means at least 1 stack is going to need to be implemented in software. So, you know, it's going to need some kind of push and poke and or push and pop. And if we assume here that BC is the stack pointer that we're talking about, this is going to be a slow stack compared to the normal machine stack, the normal return stack that the Z80 uses, because the Z80 doesn't have any 16-bit indexed address operations. So you have to break them down into chunks of 8-bit. So a software stack is going to be somewhere between 3 and 4 times slower than the built-in machine stack. That which then raises the issue: what stack should be used? Initially, in my first version of Forth, I just could not bring myself to use the built-in return stack as the data stack. It just did my head in too much. But I've come to realize that the data stack is so important and so critical, it needs to be the fastest. So therefore, I've used the return stack, the built-in machine stack, as the data stack, and implemented the return stack in software because the return stack is used less frequently than the data stack. So it's just a sacrifice that you have to make. So that's fine, except that rapidly starts to complicate the way you program. It means that subroutines don't work quite the way they used to work in a normal way, because you're essentially, when you make a subroutine call, you need to push the return result onto the stack. And the problem is that stack's already been used as a data stack. So before you can start accessing those values, the normal data stack values, you've got to do something about that return address because it's sitting there right at the top of the stack. But these things are actually quite easy to handle. But therefore need to start thinking about these things. So that's where we get to the topic of the talk. It's heavily influenced by a paper or a series of articles written by Brad Rodriguez, which I'm sure many of you have read, which is called Moving Forth. And it's a series of, I think, 4 or more articles about basically implementing Forth on 8-bit microprocessors. And he covers the whole range from 6502s through to, to Z80s and so on. And it's even if you've read it before, it's always, I find it a good one to go back to. It's just one of those things. So there are a number of threading models, token threaded, and which is topic of, I know Ken Bogue has been talking a lot about token threaded forths, is one model, but indirect threaded, direct threaded, subroutine threaded are the ones that I'm going to be talking about in this talk. Also ITC, indirect threaded, is quite similar to direct threaded. So I'm actually going to skip that and just talk about direct threaded forths and subroutine threaded forths. So just as a recurring sample, I'm just going to use this example of a colon word, a word that is essentially made up of other words. Its name is double. It has a single, it basically doubles the value that's on the top of the stack. So it does that by duplicating the top of the stack and then adding those 2 items together. A very simple example, which everyone comes across in their first learning of Forth. So you put 3 on the stack, call double, and you get 6. So direct threading, all definitions, they're slightly different to indirect threading, but I won't go into indirect threading. All definitions are machine code. In other words, they all start with the machine executing in the word itself. So in the case of a primitive words are those ones that you use all the time that you build up from. They don't call other words. That's why therefore I'll call them primitives, are just pure machine code. But we need to end that machine code, not with a return, but with a piece of code which we call next. This is a repeated piece of code, which is usually done as a macro. It could also be done as a subroutine, but essentially it needs to clean up and deal with the fact that the stack is not a normal stack. The other kind of word is a colon definition, which in the case of our word double is a series of calls to more primitive words like dupe and plus. And they always end with an exit, which is another word, which basically transfers control to the next thing. So next in the Z80 is basically a case of in direct threaded and indirect threaded, you need to have in one of the registers a pointer pointing to the next word. And essentially what next does is it uses that pointer to pick up the code for the address for the following word and put it into its own registers and advance it itself. And it's kind of clever enough to advance the pointer as well. So it's now pointing at the following word. It's basically like a program counter in a normal machine code context, but this is an emulated virtual machine kind of thing. And that's because we've had to go into this kind of world because of the use of our threading and the use of our stack in this way. The main things that I'm interested in here is how slow these things are. So you can see that the overhead of this particular operation is 55 T cycles on the Z80. A T cycle is essentially 1 T cycle at 1 megahertz is 1 microsecond. So that means we've got 55 microseconds just for this particular operation. You can see that primitives all take the form of some kind of work that happens. I've actually forgotten to mention the register pair in that push operation, but basically the duplication is pushing the content of a register pair, in this case DE, onto the stack, and the drop operation is popping it back into DE. DE is the top of stack. I forgot that in this particular slide. And colon definitions need to have some additional stuff. They need to push their return address onto the fourth return stack. Then they call this same bit of code called next. Then they do whatever they need to do inside that word, and then they need to exit the same kind of way. Oh, this will make sense, but I mean, the main thing is, I think most people are probably familiar with this scheme. The bit that is interesting from my point of view is how long these take on the Z80. This is a typical example of a colon word written using a direct threaded model. The first thing that happens when you enter, as I mentioned before, the machine code, each word definition is machine code. So it has to first go off and call a generic piece of code called enter. And then it has a data, essentially a list of references that follows it, which essentially represent the fourth program, dupe plus exit. Where I've gone with this is essentially to build up or calculate essentially the overhead that is being applied to the program and doing it on sort of a weighted basis based on the proportions and percentages of these different words. So things like dupe appear all the time, whereas other words might be quite infrequent. And essentially this would be, and this is what gets added to the total operation of a typical piece of source code. So this is based on a piece of source code. I've just basically done a frequency analysis of it. I haven't shared the spreadsheet itself. This is just summary data. And this is just an initial step to give you an idea of where I'm going with this. The main point is that these numbers, 32,000, we want them to be smaller because they represent the overhead. And we're trying to get that as small as we can. So borrowing from the carpenter's phrase of measuring twice and cutting once, we're going to code once based on measurement. This, I wish I'd followed this advice before I started my first fourth, which of course I didn't. I just launched straight into it. And this time round, I'm measuring everything before I do any implementation to try and get the fastest architecture going. And of course, implementation has been going on since then. But these are the findings. So before we get into that, I want to talk about the alternative to direct threaded code, which is subroutine threaded. The difference between direct threaded and subroutine threaded is that you don't need an inner interpreter anymore. You're essentially just representing the fourth word, colon word, as a normal piece of machine code, which is making a series of calls directly to the words that you're interested in. So we have, this obviously simplifies the model. It frees up one of the register pairs. And as you can see, they're in short supply. So one free register pair. We don't need the IP register anymore. We can just use the program counter of the processor. We don't need to have next at the end of every operation, which reduces the overhead of enter and exit as well. It could be faster. We need to find that out. It's going to be bigger. And that's probably one of the that is the major downside of subroutine threaded and why people don't usually do it on 8-bit microprocessors is because you're suddenly turning a 2-byte reference into a 3-byte reference because it includes the call opcode in addition. So suddenly you end up with 3 bytes. It also we also need to deal with the fact that now this data stack is really going to get starting to be used as a return stack. So we better start, uncomplicating our life a little bit with regard to that. So here on the right, you can see an example of what I'm talking about. Basically, call over, call cat, call XOR, and drop over, etc. This kind of thing with a series of calls is how subroutine threaded forth looks like in Z80 assembly language. I'll just quickly summarize what registers I ended up using. The stack pointer is now the data pointer. The BC register is now the return stack pointer. DE register pair is the top of stack. And IX is a temporary variable that I use. HL and A, the traditional accumulator, are kept free to be used for transient values. And I don't make any heavy use of the alternative A register, the IY register, or the alternative BC, DE, and HL registers, but I leave the option open that I might be able to find a useful way to use those. So the big issue is because you're making calls, you're pushing that return stack onto the data stack, which you're pushing that return address onto the data stack. This is just something that we don't want to leave around because it makes it hard to read the data stack. So for colon definitions, we need to transfer that address from the data stack to the fourth return stack as the first thing we do. That's the equivalent of enter colon type macro. In primitives, we don't need to go the whole distance of transferring that return address onto the return stack. We can just store it in a temporary location. So where I'm putting it is in the IX register. So I pop it off the data stack and I put it in IX, and then I use it again later. And that's fine for primitives because primitives don't call other fourth words. So that doesn't need a recursive sort of approach. We can call other machine code, but it just will not have quite as clean an interface to the data stack anymore. But you can do that. So we've got different enters and exits. When entering a primitive, we just pop the return address straight into the IX register and just leave it there because IX is not used for anything else. And then on leaving, we just jump to the IX register. In the case of colon definitions, we pop it into HL because it's more useful there. And then we push it onto the software implemented return stack, the fourth return stack. And the opposite routine, when we leave it exit colon, we just pop it and then we jump to it. So you can see that this adds essentially 38. That's actually miscalculation on that second one. It's actually 17 plus 44 plus 38. But anyway, I've got the numbers wrong on that second one. It's closer to 100. So, so here's an examples of what the code will look like. Enter prim, push DE, exit prim, and then drop, and so on and so forth. This is how you would implement primitives, dupe and drop. This is how you would implement double, which is a colon definition. We go enter colon, then we call dupe, then we call plus, then we call exit colon. Comparing DTC, you can see there's some inelegance with this, and it does use more memory. But we can see that we are getting a 25% drop in the overhead of the word. And that means on all words, it's going to be, possibly, 50% faster to implement, to execute that overhead code than it would be. And so with a distribution of prims to colons, I've got slightly different values for when it's very primitive heavy versus where it's very colon heavy. But essentially, you're seeing a pretty consistent saving of around 30% of the overhead. So it's a trade-off. One of the things about this table is it also talks about how much bigger your code is going to be. It's going to be 50% bigger. That's the downside. So you'd want an improvement in the speed for that. It's a trade-off between size and speed. STC consumes 50% more memory, which is very significant in 8-bit systems. STC is about 25 to 30% less overhead. The advantage grows as a percentage of colons relative to primitives increases. But wait, there's more. One thing that STC really gives you that makes it worth even talking about is the fact that you can inline definitions directly into the word so that you can actually just expand it, treat the word like a macro rather than treating it like a subroutine. The problem with that, of course, is it's going to expand your code even more if not done carefully. So it's a no-brainer for any kind of operation which takes less than 3 bytes, of which there are a few, like, for example, dupe and drop can be implemented in 1 byte. And it gets rid of 100% of your overhead. So while it increases, it can potentially increase your code more than 50%. And it also makes code inspection like C harder to see the definitions. I'm calling it STCI just for inline. And both size and speed are quantities that you want to optimize. You want to inline all of your really short operations, anything less than or equal to 3 bytes, no problem. And also you want to inline the most common short operations. But everything else you should do as a subroutine call. So this is an example of what the code would look like on the right-hand side, full of inline code. And it starts to look a little bit more like native compiled machine code. So these are some of the candidate words that I would inline, the ones that are most common and the ones that are the shortest. And you can see that, like, if I inline dupe, it could actually make my code smaller, but most of them increase the size of the code a little bit. And without inlining more than these really, really common ones, you can see that, like, these are hugely common: dupe, swap, over, rote. Rote's a little bit controversial because it's 6 bytes in size. Drop, minus, here, plus, character fetch, etc. These are all being done as inline. And this is to give you an idea what the code would look like for some of the most common operations. And comparing, we're getting to the business end of it. Basically, it does make your code larger, around 65 or 57% as opposed to 50%, but it does make your code faster by reducing the overhead by at least 50, in the order of 50%. So you're getting a significant, but not slam dunk. It's really got it needs to then be seen whether it's worth it, this kind of reduction in overhead. But more size gives you more speed up to a point. We need to, I basically see this as a job to optimize this further to get an optimum sort of value for this. 50 to 60% increase in size over DTC, 45 to 55% less overhead when compared to DTC. The generated code looks more like native code, easier to integrate with your other code. It's essentially a compiler, basically. It's compiling in the same way as a C compiler, but the good thing is it's 4, so it's actually smaller and neater than the C compiler, less like a virtual machine, and reduces the overhead of loops and branches because they can be implemented as native. So my final conclusion is that DTC remains the best all-round solution. It's what CamelForth is written in, it's what eForth is written in, and it still would be probably the most recommended. However, if you do want to experiment with the idea of getting that extra performance at the cost of a little bit more memory consumption, then DTC is worth doing. And that was not obvious to me before I started this. So it really was an exploration that had to be based on measurement. So STC and STCI have significant benefits, and they reduce the overheads on every word, and this can speed up forth considerably. Commonly, inline sequences should be kept short. Finding the optimum compromise between size and speed still needs more investigation. So this is examples of my forths. The one I wrote 2 years ago is called Firth, as in the Firth of Forth, which is a bridge area in Scotland. There's a great interview with Charles Moore in front of the Firth of Forth. And Z Forth is the one that I'm working on now. So in answer to Ulrich's question, it's Z Forth. And I'm still in the process of implementing that. But anyway, the only way to know for sure is to write sample code. That's one of the mantras in Brad Rodriguez's Moving Forth. And so that's my discovery based on measurements. And that's it. Thank you.
Right. Thank you very much. So, very nice talk. I've been working on Volksforce port to the Z80 many years ago. We used indirect threaded code. Very interesting that you made a review of the threading techniques. Are there any questions?
Hi, this is Christian. I have two questions. One is threading used in other VMs? And the other one, is there any relation between CPU threads and fork threading? Any concept similarity?
It's a different use of the word thread. I'm answering the second half first. So as in threading in terms of in concurrent terms, that's a different use of the word threading. But threading is used in other virtual machines. So we actually had a good talk about a Fortran virtual machine running on the DEC computers in the June talk by Greg Schmidt. That's an example of threading being used. And so I believe it's used in a number of other virtual machines. But there are different strategies, and these are the 3 strategies that are available to any virtual machine. Or 4 if we include tokens, which of course is widely used as well.
Thank you.
Boy, that really takes me back a bunch of years. Had a lot of fun with the C80, trying to figure out, cut some cycles out of routines and stuff.
Yeah.
My answer to C84 ended up being subroutines threaded with lots of inlining and an optimizer, combine multiple codes into one set of, and that cut down the size of the program. But it was slow evolution of the software as time went by. It was a lot of fun.
Yeah, I've commented that you know, in eForth we have the version 1 eForth, which has about 30 implementations, and they are all direct threaded. And then when I move it to some real applications, I released a number of Forth implementations on the eForth 2. And all the eForth 2 implementations are subroutine threaded. And then over the years, I made other implementations on newer microprocessors, and they are all subroutine threaded.
Yeah, it's interesting because you can see the reason for not going to subroutine threading for 8-bit, but it's obviously very strong once you get into bigger word sizes. And but yeah, I mean, if I was doing it on any other processor, like a wider processor, I would be doing it in subroutine threading with no question at all. It seems to be good. Peter, are you talking?
From Atle.
Sorry. Oh, sorry. Can you repeat that, Peter?
Atle.
Atle, you're still muted.
Ah,
No, you are
still
not.
muted. Can't hear you. Can't hear you, Atle.
Not working.
Not working.
Bad microphone.
Request permission to speak.
No, Atle.
Yes. Who else?
On the Z8 in 1984, I implemented a fourth natively. I guess you would call it directly threaded or whatever. It generated a native machine code, and it worked perfectly fine. And I think that is the ideal model for the Z80 and for other 8-bit architectures as well. That's all I have to say.
Yeah, well, I mean, I think the main point about going over very well trodden ground is more just, at least from my point of view, learning, but also just seeing whether there's any edge you can get, because everyone's been over this ground, right? It's unlikely that I'll find anything that's absolutely new, but I did find there was at least some benefit to increasing the size of the code.
Well, who else? Ulrich, are we? Who else is Abraham in the meeting? Is Abraham?
I am. Can you hear me, Peter?
Okay.
Yes. Yeah.
Oh, you can hear
Sean.
me. Great.
Then we follow with Abraham. Is okay for you?
Yeah, that's good. I'm going to go ahead and share my screen now.
Mm-hmm.
If that
Great.
works. Okay. Hopefully you can see my screen, and I need to minimize that.
Yes, we
chat
can.
box. Okay. Very good. Come on, Google Slides. There we go. Okay. Okay, thanks, Peter, for inviting me to give this talk. I know it's been quite a long time coming. For those who don't know, I'm Abraham Muller. I go by John, and today I'm excited to share with you just really the beginnings and a very simple proof of concept of a ESP8266 light meter and eventually a data logger that relies on Puniforth. It's a much more application-focused talk as opposed to the workings of Forth like John was giving. Okay, so my goal is to build a compact Internet of Things capable data logger that primarily would help with health and home automation, but I can think of other uses such as, citizen reporting of weather and gardening. The idea here is this data logger would collect in real time light, temperature, and humidity through a solar cell and a DHT combined temperature humidity sensor. I found reducing humidity has greatly improved my sleep quality, so I have a lot of interest in measuring humidity in different parts of my apartment. Certainly, DC's had a heat wave for the past several days that's just passed, and I've noticed its effect. So that's one possible use. Another is home automation. Already, air conditioners have some aspect of a homeostatic or negative feedback type of control. They have a hygrostat and a thermostat that will turn off the air conditioner once a certain temperature and humidity are reached. But at the same time, that's just right adjacent to the air conditioner where the temperature and humidity are being measured as opposed to elsewhere in the room. So there's more that could be customized with that, and definitely for lights. There's my manual feedback. It gets dark, I need to turn the light on. It's light outside, so I turn the light off. But automating that could help a lot with energy use and, again, health and so on. I failed to mention that this can be beneficial for gardening. Say you have an orchid that's really picky about light and temperature and humidity and nutrients. You might not get nutrients from this. You probably could hook up another I2C sensor or something to do that, but you could get that data in real time and tune your greenhouse or whatever garden. And I've also heard there's citizen meteorology. You know, you can collect temperature, humidity, and light at your particular location. Anyway, so why use an ESP8266? It costs $5, super easy to power. I can hide it in a little box, and it's Wi-Fi capable. And why puny forth? Or why forth in general? It executes very quickly. Debugging I can do interactively and a lot quicker than, say, with C or Python and so on. And of course, it has built-in words for reading from GPIO pins or the ADC, which I'll show you here, so I don't have to reinvent the wheel. So what did I use as a light meter? Well, most of you would probably think, you know, why not use a photoresistor that will decrease in resistance given light, or, you know, a photodiode, a transistor that increases gain as light is added. But instead, I chose to use a solar cell. And I'll be honest, the primary reason is I had one hidden somewhere in, you know, a junk box, but there's other benefits too. It's most responsive to solar radiation as opposed to light inside a room, which can be helpful for various applications. And there's no need for an external voltage. You just read the voltage that's induced, which you can see is proportional to luminance as well as the current output. There's normally 3 and 6 watt solar cells that I've seen, and the voltage, as we'll see, is within the range that the ESP8266 can tolerate. So again, voltage here is proportional to the intensity of light. It's an incredibly difficult interface. You connect the negative wire to ground and then the positive wire to A0 on the node MCU or T out. So interfacing is pretty simple. And then as far as routines, you know, we think in forth in terms of factoring problems, and I think a lot in terms of domain-specific languages. One is for reading data, so having words that will read light from the solar cell, and then also for temperature and humidity. I don't have it yet, but I had a $2 DHT11 coming in the mail that I'll interface, and puny forth does have a library to handle that you know, I'm going to study thoroughly so I understand the internal workings. There's words for printing the data in a nice tab delimited format, fetching network time. So there's a network timestamp and an uptime stamp, like you'd see in Linux, as we see, with more resolution than network timestamp that goes to seconds, at least in this implementation. And network communication. The goal here is eventually to have some socket where a server could connect to the socket and then get in tab delimited format. Network time, uptime, light in terms of voltage, induced voltage, and then temperature and humidity, and then process and plot that data and start building models for, you know, different times of day and times of year and so on. So the way I'm interfacing this solar cell is through the ADC. Fortunately, there's an ADC read word that Attila implemented in puny forth, and this reads the voltage at the T out pin, which is from 0 to 1 volt. But as you noted earlier, I'm connecting the solar cell through the A0 pin, which goes through a voltage divider. And oh, someone has a question. Okay, I'll keep going. Anyway, and then the RF pin enabled. Anyway, so it reads voltage from 0 to 1 in 1 in 1024 volt increments. So I have pretty simple words right now. This example is just measuring, actually, excuse me, not 1 second intervals, 0.1 second intervals, measuring light in terms of voltage over a 30-second time period at a 0.1 second interval. I have 2 global variables that you would set for duration and interval for measuring, a word that converts this to number of iterations. I've further refined this, but a word just to get light at a certain time point. This will find the uptime in milliseconds, tab, and then read from the ADC, and then carriage returns, so quite simple. And then this measure light word that will convert into iterations and then go through a do loop and add every wait an interval and then get light and repeat. And we'll notice that because I've added network time, and that has some ping time. It's not quite, say, 100 milliseconds. It might be 190 milliseconds because it has to contact time.google.com to get the time. So essentially the way you do this is set a duration, milliseconds, 30 seconds, 0.1 seconds as the interval, and then measure light for that time. So this is hello world, not in terms of programming, but just in terms of, you know, testing the hardware with your hands, literal hand waving, not making up an explanation for something that has maybe little or maybe a lot of relevance, but actually waving my hand over the solar cell, which I'll show you again after I'm done with this. I put my solar cell right on the windowsill and then started measuring for some time period, and you can see there's about 0.09 volts induced, and that was in the afternoon, so decently strong light. I put my finger on the solar cell. Suddenly you get to this trough here. I move the solar cell under the air conditioner, and there's some vicissitudes when I move it back and forth, but the amplitude of light goes down, and then I put my finger on the solar cell again. Again, this is just units of voltage. Eventually I'm going to calibrate this in terms of light intensity. Okay. I've added recently an enhancement with network time. Again, it would be useful to have a network timestamp. Again, I don't think I need to put in the overhead to process this and forth. I could do that, in a spreadsheet or in on a server with a higher level programming language. But anyway, it's pretty simple. There's an NTP library. I have my ESP8266 in client mode, so it's connected through DHCP to the internet. It can access network time through time.google.com, and I can print network and uptime as timestamps. So the next steps then are going to be to do experiments, test this in different rooms and see how light differs, especially with lights off. So just I'm pointing towards the north, so I guess that's not super as interesting as being west or east. But anyway, so light that comes in from windows pointing to the north, different locations of the room, turning lights on and off, and seeing what intensity corresponds to me thinking I need a light on versus off. Building light profiles, again, depending on location and time of year. And the most important thing is calibrating against luminance or light intensity. And there is a meter on my phone that can measure that from the camera. Then for improving the data logger, again, the DHT11 will fit on the breadboard. I'll show you pretty easily, and that will add temperature and humidity at the same location. I mentioned network and uptime stamps. Making a TCP socket, I have to read more about that. So there's a data stream. And then one other thing, and I think everyone will really love this joke. There's a famous, I find funny, hopefully other people do too, joke that the S in IoT stands for security. Yeah, so you don't want to connect this to the internet and then have a free port for someone to break in. There has been a power line outage that I think was traced to a Wi-Fi coffee maker. So Wi-Fi coffee makers are bad is the lesson from there. Anyway, so this would be just on the local WAN and isolated from the internet. And with that, I'll just acknowledge Attila and Jos, who developed a floating point stack that should be really helpful. So, I could have decimal value intervals instead of limiting to milliseconds or having to put intervals in milliseconds. Peter for inviting me and his help. And I think now I can do a quick demo yeah, it looks like there's time and it'll probably be entertaining. Yeah, instead of using my standard laptop webcam, I have a webcam that can rotate here, and you can see air conditioner and the little assembly over there. And I'm going to go ahead and stop sharing. and share a different screen that's connected to the ESP right now. Oh, share. Okay, so hopefully you can see my terminal window. And I'll show you the solar cell. Oh, did someone say something? Okay. Yeah, so that's the solar cell there. Oh, here we go. Oh, it has a little bubbled window, I guess, that concentrates light. And again, just some jumper cables connecting it to the ESP8266. I'll put this back in the window and do some hand waving here. I can set 60,000 as the duration, and then 1,000 as the, oh, that's not going to work. Get rid of that. 1,000 as the interval, and we'll see. Okay, so we can see on the left the network time, the uptime, and then the light intensity. I might put my hand on that, and that you can see, you can see the response in real time, coming back to normal and lower. And again, ideally, this would be on a TCP socket, and then some Java code or Python or something on a server would process this to give you a trace in real time, along with temperature and humidity. And then I'll know, 40 to 60% humidity as the experts recommend for sleep. Empirically, I can show for an N of 1. Anyway, so thanks for listening. And if you have any questions, feel free to ask.
Fantastic.
Great. Thank you very much. Amazing.
I want to add something to this presentation of Abraham. For people who join us for first time, for Force, what is Force? Force is installed inside the ESP8266. So you have an interpreter. Abraham is working interactively with this Force over Wi-Fi and Internet. And what happens? Of course, you can have today MicroPython installed in this ESP8266. But what is the problem? When I bought one of these chips 4 years or 5 ago, I had Lua installed in the chip. So I wanted to make home automation with this. And I had only 2K of free RAM to work with my program. In Lua, 2K is nothing. You can switch on and off a relay, but nothing else. You can do absolutely nothing, almost very few applications. So I went to the internet to look around, and I found Force. Oh, Force is there. My old beloved language. So this is why I came back to Force. And people who have MicroPython in these things will understand this problem. This is the difference from Force to other languages. In Force, I got over 200K free of programming space in this chip. This is very important. This is the difference, because in MicroPython, okay, you have an interpreter, but what happens with the memory?
Right.
Yeah, absolutely.
Yeah, thanks for the remark, Peter.
Yeah, thank you for your explanation. Thank you.
Are there any questions to John?
Abraham,
John. Yeah. I might not have got it. Do you have this available somewhere on the net so we can look at this, or is this still work in progress?
Oh, it's a work in progress, but once I'm all set, I'll add to my GitHub repository.
Yeah, that would be great.
Details and the diagram and everything.
Mm-hmm.
Yeah, definitely. And thanks for Peter. Thanks Peter for adding that. It's pretty simple to flash the ESP8266 and plenty of RAM free. Oh, and it also does multitasking, so you can have multiple words running at the same time.
Yeah, very nice. Yeah,
Okay.
and the nice thing
Yes.
about the 8266 is that you can also have some kind of power down mode. So it's much more suitable for these kinds of application than the ESP32. And as long as you don't do the radio transmission, and you can go into deep sleep mode and really make battery-driven applications. So that's
Nice.
also nice.
Okay.
Ulrich, are you ready then for your presentation?
I'm
Would you
ready
like?
I'm ready for my presentation. And let me see, I share.
Okay, Ulrich Hoffmann from Germany will present to us tutorial of force data structures arrays. After that, he will show us Holon force and ESP32 force integration.
Right, so let's see. I hope you can all see my first slide. I'm intending to have a series of tutorial talks where I will capture best practice, and we're going through data structures right now. 2 months ago, I talked about structures and how to name the fields in the structure. And today I want to talk about arrays. And interesting enough, I thought about how to structure the talk. The first slides are actually the same, talking about force and features and force and memory. So I just very shortly jump over them, saying some words to it, but then we want to look at how to define force arrays. And the secret in force is that you have to manage the memory by yourself, but you can do this very easily by defining appropriate words. And but you have to know about what problem you want to solve, and in the case of arrays, it's you have to do the address calculation, either explicit or you do it implicit, hiding it in some words. And you can also define simple arrays by what we call defining words. And we will look at these simple arrays and also at arrays that work more or less the same, but do bounds checking. So if you use indices that address elements outside the array, you would get an error and error message. And then we come to a conclusion. So what we face with force often from outsiders, that people that are new to force, is, well, I would like to do this and this feature, and does force support this feature? And then if you ask a seasoned forcer, then he will tell you, no, it doesn't, because it's application specific, you define it on your own. And so that's the reason I'm giving these kinds of talks, because then the question for a beginner is, well, and how? And this is what I want to answer. So we looked at structs 2 months ago, and today on arrays. And the idea is you have to know what you do, and you have memory in force explicitly available that you address with appropriate operators, and you have to build your data structure yourself. And you have to have that know-how of how to do that, and use the appropriate best practices. And so if you have a string in force, for example, like force 2020, that's a slide that I showed last time as well, then it's just laid out in some force, most of force use this kind of layout as a counted string, where you have the number of characters in the string at the beginning in the first byte, and then you have a sequence of bytes that represent the characters of the string. And then you can say count on the address of the string, and then the start address or the address of the first characters put on the stack, and also the length. You can use the operator type to display memory starting at some address with a given number of characters, and so this will output the appropriate string. And if you do your own data structures, then you have to do the management on your own. And today we want to talk about arrays. You use this using the basic forth operators, and so you have to access memory via fetch and store, or character-wise via cfetch and cstore, and you have to allocate memory, which can be in the dictionary. That's what we will use today. It can be in ROM and RAM. We will not talk about the difference of RAM and ROM today, but that would be an interesting follow-up talk, of course. And so you can allocate a given number of bytes in the dictionary, or you can lay down appropriate values using comma or C comma in the dictionary. And so variable, for example, is just create a named memory location and then allocate one cell of memory that you can use to fetch and store values there. So let's come to arrays. So what is an array in the first place? It's an indexed collection of elements. So every element has an index, and you are going to access the value of that element by using the index. And so let's think that we doing a table of squares, and let me see, I don't know whether you see this, so I'm minimizing the sidebar that I have in Zoom here that's on top of the slides, so I'm minimizing that one. And so let's, as an example, let's think we have a table of squares, so square of 0, square of 1, square of 2, and so on. It's 1, 4, 0, 1, 4, 9, 16, 25, and then the array should end. So if we want to access where the dots are on the right beyond the memory that is allocated for the area, that's not legal. So that either gives us unreasonable values, or the program might crash, or we later on we will get some memory protection by doing bounds checking, and we get an error message. So what we need to do this, of course, is to allocate sufficient memory so that we can store all the elements of the array. And then for accessing the elements, we need to do the so-called address calculation. So we take the base address, which is the address of the first element, and then we take the index of the appropriate element, multiply this with the size of each element. In an array, all elements have the same size. And then what we get is the element address. So as an example, if we want to do the address calculation for the index value 4, then we have the start address. We have to multiply 4 by the number of bytes in each cell, which is 4 in my implementation. That's probably wrong here if these should be addresses, but okay, assume it's a cell-based thing. Anyways, so you have to multiply this with the size of the elements, and then you add this, which means from the base address with the given index, you get to the address of the appropriate element, and then you can fetch and store values there. Yeah, and so in Forth, you allocate a table like this, either using comma, initializing it on the fly, or during compilation, or you just allocate uninitialized memory, and then your application later on has to initialize the value appropriately. So let's see how this accessing of element 4 here works. Suppose we want to initialize this and place a 16 in that memory cell. So what do we need to do? Yeah, we need to take 4, multiply this with the size of the cells, and then add the base address SQ to it, which gives us this address, and then we store the 16 that is on the stack here. We store this in the appropriate cell. So that's doing explicit calculation. Our data structure is just the base address, and we do all the address calculation by ourselves. And if we have more than a single array, then we have to do all the address calculations of all the arrays over and over again. So the fourth way to do this is actually doing factorization. So address calculation can be some kind of operator. And the typical operator that you can use is mimicking the bracket notation of other programming language using the box operator if you want to, or you can call it content of. It's the index operator. And so before we said 4 cells SQ plus and supplied SQ as the constant and 4 as a constant and do the calculation all over the place. Now we are factoring the calculation into this content operator, which essentially swaps to get the index, multiplies by the size of the elements and does the appropriate add. And then we don't do the address calculation anymore at all places, but only in the definition of the operator. And we, for example, use something like this. Instead of 4 cells SQ plus store, we say 4 SQ content of or address of store to do essentially the same calculation. Well, that's great. So it's explicit with a good factorization, and we have an operator that does the address calculation and captures this idea in a single definition. So that's quite nice. What else can we do? And that's a very amazing thing that I, while rereading Thinking Force, discovered. There was a discussion about arrays and interview that Leo Brody played back things that Charles Moore reported, and he did the same thing with the calculation, but he did with factorization, but he did a redefinition. So that's really strange. We have the fourth property that we can redefine words, but the old behavior, the old semantics of the word is still active. So this defines a new word with the same name, but it's actually a new word that can make use of the old word. And so we can also define SQ to do the address calculation on its own. So this SQ that we used before just left the base address on the stack. But now this new SQ uses the old one that leaves the base address on the stack and does the address calculation. We could also use the box operator there. And then SQ does the address calculation. It takes an index and it calculates the address of the appropriate element. And then if we do this, then we can do 16 for SQ store. So now always SQ takes an index and does the appropriate calculation, yeah? Which is quite nice. No defining word now up to now. And so if you have just a single array, then it might be reasonable to do it like this. Instead of spreading the address calculation all over the place, do a redefinition and then use the self-indexing to do that. Right, but if we have several arrays, then you might want to define them to have a common behavior and do the appropriate address calculation. And if we use defining words, we have two parts. One part does the memory allocation and gives the new defined word a name. And the second part, the does part, defines the common behavior of all the new defined words. And if you then do the calculation, the definition like this, we define a so-called defining word array that takes the size of the array in cells and allocates appropriate amount of in the dictionary. And the new defined array words, they are all self-indexing. So they take an index and do the appropriate address calculation on their allocated memory so that you get the appropriate element address. So you use it like this, 6 array SQ, yeah, which defines an array with 6 cells of memory. And because of the does part, it does the automatic indexing like the SQ that we defined before, not just putting the base address on the stack, but also doing the appropriate address calculation. And then you can use it like before for SQ store. But if you want to have another array then you can just use the array defining word to define it with the appropriate size. So that's great. And this is always the balance that you have to find. If you just use a data structure once, then it might be easy to just use colon definitions to define the appropriate behavior. But if you want to have multiple of them all with the same behavior, then a defining word is probably nicer. Another thing that can help us here is with a defining word, we can also have a modified common behavior of all the array words in that it can check also the index. So I'm defining, instead of defining array like this, I define array like this, which is, well, somewhat more complicated. But now what this array does, instead of just allocating the memory of the array, it also lays down the number of elements that are in the array. So it provides bounds checking. If I use an index that is out of bounds, then it can alert me appropriately. And for this, an array needs to know how large the memory that is allocated for it is actually, so what size it has. So instead of just doing cells a lot as before, we're doing a dub comma, which puts the 6 here down for 6 elements of the SQ array. And the behavior of the new defined words are like this. So essentially, they are also doing swap cells plus as before. But now in advance, they check if the index that is on the stack is actually a valid index. And it does so by comparing it to the size of the array using an unsigned compare. So if I come with -1 as an index, this will be considered as unsigned numbers as the most largest unsigned number, and which is way off the bounds. And so a single compare here is sufficient to do this. If I come with a 7, for example, then it's clear I'm out of bounds. And if I'm coming with a 6, then because I'm negating this, that's still an error. And so I'm doing things here that are similar to the calculating conditions that I've been talking a couple of months ago. So you do the comparison, and if it's invalid, then you will have a -1, all bits set on the stack. And if it's valid, you have a 0 on the stack. And then you end this with -24, which happens to be the throw code in standard force for invalid numeric argument. And either you end up with 0 or -24. -24 if you're out of bounds, and 0 if everything's fine. And throw will just consume the top element. If it's an error, it will do appropriate error handling and throw that error. And if it's a 0, then it's all is fine and we continue. Then we need to back up from the parameter field address of the new array, the start address of the allocated area, skip over the number of elements that we stored there, and go to the first index position. And then we can do our normal index calculation. So the advantage of this is that you can use the array word as the previous array defining word. You can just define a 6-element wide array. It allocates another element, the size of the array, for doing the bounds checking, but you use it just as before. You can just say 16 for SQ store, and you store 16 in the appropriate element position, which is now 1 cell further than it used to be before. But because the address calculation is hidden in the word, that's not an issue, because the word knows where to do the appropriate, how to do the appropriate address calculation and skip over the length field. But now if you say 36.6 SQ store, then it finds out 6 is actually not U less than 6. because it's equal to 6. And this calculation will give us -24 throw. And depending on the force system that you have, you can also think of an abort quote clause or whatever you do here for error handling. But if you have a system that has catch and throw also in the interpreter, then that's a reasonable way to do it. Then the program will abort with invalid numeric argument, or if you have some error handling in place, it will just alert the higher level procedures that you have an index out of bounds error somewhere when accessing this. And then you can inspect the return stack to find out what actually went wrong. Of course, in an embedded system, you never want to output invalid numeric argument and then the system will stop. You always want to have some kind of error handling and resume operation as best as you can. Right. So this comes to my conclusion here. We looked at force arrays and we saw that you have to know about address calculation and how to represent arrays in memory. And if you know this, base address plus index times size is what you need to do. Then you can program this in force in several ways, either explicit or every time you need this, or you factorize this in a content of operator, or you have it in the does part of a defining word. These are the things. And also you can do bounds checking if you want to. We can also think of a box operator that does the bounds checking. So there are many choices that you can do, and using one or the other is depends on what you actually need. Do you need more than a single array in your simple application? Yeah, then have a defining word. If you just have a single one, you can do the calculation explicit. So when we talk about the tutorial series, we saw structs 2 weeks ago or 2 months ago. We talked about simple arrays and bounds checking arrays and explicit, implicit calculation of the doing the address calculation. But there is more to arrays. You can use this bounds checking mechanism to also have something that I call automatic resizing arrays. That is when you access memory out of bounds, then a mechanism can, of course, that we saw, can detect this, but then a mechanism can reallocate the memory of the array, copy over the elements that you already have, and do the appropriate address calculation for you. So maybe your array will double each time in size until it fits, which is nice if you don't know about the actual size that you need. So that doing some use will resize the array appropriately to the needs. Of course, you will have some upper bounds where you signal errors. Anyways, yeah, right. Another topic that might be interesting for some forthcoming tutorial is RAM-ROM distinction, especially in embedded systems. You have flash or ROM and structures that you want to place there, for example, constant tables. And you have other data structures that you want to place in RAM because you want to modify during runtime of your application. And then it's not good if they are in ROM because it's read-only. Yeah, we discussed a lot about how to have a view of the standard operators that we already have and maybe give them some meaning of whether they are in RAM or ROM. And I can talk about that in a future talk. And of course, you can use arrays and records to also do objects. If you start storing execution tokens in arrays or in records, then you can do things like a method can do an indexed call of the execution token that is in there. And as well, other data structures that might be interesting are enumeration types, where you just give names to numbers. So you can use them more easily and read programs more easily. So that's the conclusion of my talk. And I keep this, so maybe there are some questions for this already. doesn't look like that.
This is good stuff.
Yeah. Thank you. Thank you. As I always say to my students, so maybe questions come up later. And then offer, of course, that you just send me an email to my address. It's in the chat at, more or less at the beginning. Or I can just revert to where we were. So uho@xlerp.de.
Ulrich, did you think about two-dimensional arrays?
Mm-hmm. Yeah, yes, I did. Of course, the key is if you are in Forth, you have to plan the memory of your data yourself. So the address calculation function becomes more difficult. Yeah, you have two indices, and one is the size of the row, and another one is the size of the element, and then you have to do a similar calculation. A similar calculation to the one I presented to get to the element in a matrix. Yeah, so yeah, that's possible. But all the ideas, doing is implicit or explicit, or redefining the matrix to do the auto-indexing. That all holds for matrices as well. And there are also different ways to store elements in a matrix, because you have the address calculation function in your hands, because you program it by yourself. You can do either way. So having pointers in a one-dimensional array to other arrays, that's one way to do it, or just having the elements in a row by row order in memory. So that lots of things that you can do, and what you want really depends on the application. So if you want to flip rows, for example, in an easy way, then an array of pointers to other arrays is much more nicer, because then you just need to flip pointers to flip the rows. Yeah, really depends on what you need to do.
Okay, thank you.
Sure. Right. Are there any other questions? Good. Thank you very much for listening. And then I would like to switch over to the second talk, and let's see what is behind this. So let's see, this one also goes away. And there is something very nice. So here we go. The top window that we see now is the development environment Holon Code that Wolf Weigart of Switzerland has developed over the last 30 years, I guess. And it's the latest incarnation of it called Holon Code. You can download this on GitHub and do your own experiments. And early versions of Holon were developed for use under DOS for the IBM PC at that time, and also for embedded systems using Motorola HC6811 chips. And the nice thing about Holon is that it structures your application in a hierarchical way, as we see here. So you have chapters, you have sections, and you have units, and within a chapter you have a collection of sections, and within each section you have a collection of units. And this maps very well to Forth programs, which means these are application areas, sections are parts of a file, so to say, and then you have collection of words within each section. Yeah, and and then it's very easy to move around and find appropriate places by just a couple of keystrokes. You can do this, and also if you go there, you see things are, let me see how this is, things highlight here, and you have hypertext reference of your things. So if I'm clicking here, then I'm jumping to the goodbye word that we have. So automatically Holon indexes the the source code that you have. So you have very easy navigation of within your source code of your application. So, right. We had old Holon work with embedded systems, these HC11 boards, and I thought it might be reasonable to also use this for development of embedded system nowadays. And so what I thought is maybe I can combine Holon with ESP32 force. I don't want to say a lot about ESP32 force here because everyone knows this here because it's a quite popular system in this group. Right. And so what Holon does for interactive development is that if you have a word, and let's see, a word like this, for example, and let me see, yeah, a word like this here, for example, then you can just go, it has an integrated editor, and you can just go ahead and modify it in the editor. And if you want then to add the modification that you did to your application, you just click on the load button here. And this is essentially prepares a file with a modification, and the system that you are going to program is supposed to pick up this modification and integrate it into the application program. That's the way that the modern things work. And then you can develop web pages with this, or desktop applications using Tcl, for example, or using Holon Force that Wolf Weigert also provides. And I thought, yeah, it would be nice if we can use this with ESP32 Force. And so what you see on the left is a running application. Yeah, and you see it says hello Holon code and ESP32 world. So that's my hello world program. And then it says goodbye, and there's a running counter. And so this is the structure of the program. It has the demonstration, and it has here the variable occurrences that is defined and initialized. And if I'm reloading this, because I said, oh, maybe I'm saying, I want to have this as 500. So it starts at 500 and I'm pressing load, then Holon writes out the appropriate program modification, and the environment that I built picks up the modification, brings it into ESP32 Force that is running on the left inside a loop. So what is actually happening is welcome is done in a task, doing appropriate outputs all the time. Let me see. So that's essentially the loop that we see there running. It does what it says welcome, then it does says I'm doing a greeting delay of milliseconds pause, and then I'm doing this in an endless loop. So that's for demonstrating purposes. And I can now modify the running program here. Which means I can go here and say, okay, no, it's add Force 2020. So maybe world here at Force 2020, and then I say load, and we see a little bit magic that's happening there, and then it loads the definition and works in a way that it replaces, unless it replaces the old definition with a new one. Different from what I've just been talking about with arrays, where we do redefinitions and the old definition stays intact and is reused. If you program with Holon and you do modifications, you actually want to replace the old definition with a new one. And there needs to be some capabilities to actually do this. And yeah, you can do this with a single button, to replace a definition in your code. So you have your application running on an embedded device, and if you want to modify it, then it will actually, you do the modification in Holon, you think about the structure of your program and your application in Holon, you do the modification, and as soon as you want to make a modification active, you press the load button. And the second window that we have here is the so-called monitor. And this is the one that observes the file that Holon writes and it detects the changes and does the appropriate thing. So and then I'm changing this again, and we have a look at the left bottom. I'm doing load, and yeah, you see the change. It says I detected a change in the Holon mon file. This is how it's called. And then this change is transmitted to ESP32, replacing the old definition of hello, changing the running task that is running on the ESP32. So it's actually changing the running program. So that's this. And in the background, we see it's a multitasking system. So it's not only that we have this output here and the interpreter that accepts changes to the program, but we also have Blinky running, which is a blink task. And there's a variable blink delay. And I don't know if you can see it blinking. I don't know if Zoom makes it go away, but here on the top, there's a LED that does blinking with about 1 blink per second as it used to be. And now if I'm changing the blink delay here and I'm reloading this, then the appropriate task changes and my other task will just run as it was before. Yeah, so we're interactively changing parts of my application, which is a multitasking application, and I can change things. Of course, you have to know what you do. It's limited. If you change fundamental structures, then just redefining a single word is not sufficient to make the system still working. But it's very nice. You can do interactive programming in this structured view of your application. And that's actually very nice. So, and now how is this done? I have drawn this diagram. So on the left, we have Holon code, the viewer, the browser that we saw for the source code. And whenever you press the load button, it generates a Holon mon file with the appropriate changes. That's the source code in the unit that we changed. Then there's the force monitor that observes the Holon mon file. And whenever it detects a change, then it transforms a little bit and then it uploads it to the ESP32 target. Yeah. The top window on the left that we saw, yeah, this one. Yeah, that's the terminal window. That allows me to see what output messages the ESP32 target actually does. That's good for debugging, of course. If there are any error messages or statistics or whatever I want to do. Not necessarily required for doing the program development because you do the uploads by yourself using Holon this way. And of course, then you need to prepare the target in a certain way. And I structured the integration in 2 parts. One that I called library source code. That's all the definitions of your application that you don't intend to change. So that's not the hot part of the application. And you load this by a script in advance. And maybe you also put this in Flash. So when you reset the ESP32, it's readily available. And the second part is the application source code. That's the part of your program that you want to change or where you're currently developing it. There's also a script that does the initial load of the application source code so that the application can run on the ESP32 target. And then once you did this, so you do this once for preparing the Flash. And if you have a new session, then you go and load the application code. Your application is running. And then you solely work from within Holon code to having the structured view of Holon to actually see how the application is structured, and you can move around and have a look at how this works and understand what's going on. And you just work, and if you do changes, you press the load button to modify your application. If it crashes, yeah, which certainly happens if you do some programming errors, if it crashes, you just need to reload the demo application source code so that it runs, because the library code, as I said, is probably in Flash. So no way, no need to reload this. And this can all be done with some overall script that does the appropriate loads and prepares your target. So you just go there and say, I want to develop, and then it loads the application to the target. It starts Holon to do this and present your application. So you have the source code down here, and you also have documentation areas. So if we go here and have a look, then there are some places where you can also have documentation and have a look at what's going on. Like you see, there are some comments in here as well. And these are just for documentation purposes. If you press load, they are never put in the HolonMon file nor uploaded to the target. So also upload is quite fast because it doesn't have any comments in it. Right. Yeah. So that's what it is, and I intend to use this for my next ESP32 project using ESP32 Force, and have a and doing structured development with Holon code on the ESP32. That's what I want to demonstrate as my second part, and I'm happy to answer your questions. Thanks for listening.
Fantastic, Ulrich.
Yep, thank you very much. So, are there any questions?
Yeah, I have a question. This is Jonas here. And I looked at the website for the Holon Force. It seems to have been a terminal application before, like ANSI. I don't know what language it was written in, but it's I don't know if it would support Linux without running in a DOS box and so on, and without the graphical environment and TCL/TK, which seems to be the option there. Do you think about that?
Yeah, so this version that I'm currently using here uses tcl/tk to use this, and if you want to use Holon code, then the best guess is to start installing ActiveTcl, which runs under Linux, under Windows, and also with macOS. And then you can use Holon. And then there's for the ESP32 integration, there's my additional repository to use that one. Does this answer your question? You can also use DOSBox and run Holon on Linux, the old DOS-based Holon there. Also the HC11 version runs there, and so Holon is public domain now, and the systems are available. You can use also the DOS versions, and I've been using this. Yeah, and interesting enough, Holon itself is developed in Holon as well, so it's not just a simple exercise.
But is it open source, or the source is not available?
It's open source. I think it's 3PL based.
Okay, all right. I'll check it out. Thanks.
Yeah, you're welcome. Are there additional questions? No. Then...
No. There is a question.
Yeah, Christian, you could bet. Yeah.
He was writing.
Okay. Yeah.
Okay.
I cannot follow the chat while giving the talks. Yeah, you probably discussed lots of things there. I will revise them.
Okay, could
Christian,
I go ahead?
Christian, go ahead.
Okay. Is the automatic code modification creating multiple definitions, or is it changing the live definition?
Yeah. So how I actually do this is yeah, maybe we can have a look at hold on. Let's see if we get this. Anyway, I'm just explaining. So there is, or maybe it's down here. Yeah, that's down here. So what you do is this is what is in the HOLON-MON, the modification that you do, and when you press load. And the transformation that I've been talking about is that it adds revise at the end. And revise is a word that I've been written for ESP32 force. It takes the latest definition word, the defined word, finds out which name it is, and then assumes there's another word that's called the same, and it replaces the other word with a new one. Yeah, and by this you can have the old way force works with redefinitions if you just do normal colon definitions, and you can have the new word way to work if you use revise. It will just replace the old definition with a new one, and then it hides the second header, so to say, so that you can repeat this process over and over again. Of course, this consumes some additional dictionary space. The old dictionary space is of the old definition is still occupied. And if you do multiple revisions, then new definitions pile up. But I didn't want to rewrite ESP32 force to do an alternative memory management. I just wanted to have it like it is, because Brad is just doing such an outstanding work in developing ESP32 force, and I want to benefit from his work. So I'm using his system unmodified and adding up on top of it. And that's what I came up with. So revise allows me to replace definitions that he has in the system with new definitions. Of course, if you revise something that is essential to ESP32 force with something that is inappropriate, then the system crashes. Yeah.
And one last question. I really wanted to use HOLONs with any embedded system for the last 5 years and could never figure out a way to do it except with the HOLON Fort that only worked on PC. So looks like you have a solution for the ESP32. Do you have somewhere a procedure that shows how to obtain what you just have?
Mm-hmm. Yeah. This is essentially the README file here of the HOLON code ESP32 integration. And if you look at my GitHub page, then you find that repository. And it explains how the structure is, what ingredients you need, how you cook them to make this work. Of course, as always in force, you have to know what you want to do and you have to adapt the things. So it's not a push button solution, but I explain all the parts that you have there, and you have to take it and adapt it to your needs. And I don't know your needs, and you have to make it work for you appropriately. Yeah, but it's HOLON code, it's the target that you have, and I have some scripts that you take and modify to load your application appropriately. And you find also the extension to ESP32 force that does the replacement of definitions. So all the parts are there, and you can start using just the demo program. And if it works fine with you, then you do the steps on your own.
Where do I find the document that you're showing us presently?
Yeah, I'm putting this in the GitHub in the chat. So it's the GitHub repository. I didn't actually prepare this, but let's see. We find this very easily. Yeah, I put this in the chat, and then you can see this appropriately.
Thanks a lot.
Sure, you're welcome. Right. So, are there other questions? Not the case. Thank you again very much for listening. And so I'm a little bit in doubt how we proceed because we are using a random schedule today.
I am ready, Ulrich, for my talk.
So our next speaker is Peter Forss, and he will talk about Forss professional applications because he used Forss to control CNC machines for many years. And I'm very happy to hear about that. And yeah, I'm very curious of what you can tell us. Peter,
thank you,
please
Ulrich.
go ahead. Yeah, we see your slides.
Excellent. Well, this is my presentation about Forss language and CNC machines. I will talk about the Forss I wrote for machines in 85 to 1998. We sold over 2,100 installations of these systems to large companies, car, aerospace, electronics, small garage companies, scientific labs, atomic energy, optics, universities, etc., etc. So, Forss, everybody knows it's a language, but what is CNC? CNC means roughly computer numeric control. You see here a mill and a lot of numbers and coordinates. What are the types of CNC machines we normally use? We have here the lathes with a controller you see in the front, a mill machine, and a laser plasma cutter or any other machine. We have also drilling machines and bending machines, and also robots. Machines move by coordinate numbers. You see here a rough diagram with the stock of material and a mill. So you have here 12 minus 12 in one axis. Probably this is the x-axis. The y-axis is minus 3. And you have a minus 2 on the vertical axis. You see here the 3 arrows. This means we use a lot of numbers to move a machine over space. And we use the controlled motors, servo motors or stepper motors. And for this, a computer is the ideal mechanism to deal with all these enormous large quantities of numbers. So my story is about how I got and how I entered into this business. No, I wanted to develop a machine to mill my PCB prototypes. Firstly, but in 1985, CNCs, professional CNCs, were very expensive. We are talking about only this part of a machine was over $30,000. They also didn't have these fantastic panels we have today. They didn't have graphics. This was a very unsophisticated controllers, but the technology was in the beginning, so it was expensive. So I decided to go along with my own design. I had the experience. I was working with labs and a lot of equipment. And I had a 68K computer which I transformed into a CNC controller. I wrote all the algorithms for CNC, and this demanded a lot of time. It began in 1985, but it took me 2 years. And here you see the first printed circuit board I was able to mill in this machine. Of course, in that time, there was no internet. So I did all alone. And with the books, here you see the fantastic book I found, among other, I will show you later. Why force? Well, I will explain now. Force fits, in my opinion, like a glove for CNC. Also for robotics. This is the two fields I feel force is very, very powerful. You see here some examples, lead on, lead off, how simple I talk with hardware. In that time, I used not very sophisticated controllers. As you have seen, this was a 68K controller, but they were not so fast as today. So we had to work, of course, all in assembly. All was assembly code. There was no way to talk with these fast moving motors and mechanics, etc., with a high-level language. We didn't have these solutions. I found in Force that I was able to write directly in assembly language. This was fantastic for me. I started inside my algorithms. I was able to write code and define a word, and then end code, and then I continued with high level. I could mix. You see here an example of an old system of end of the 70s and beginning of the 80s. You see here code, key, mixed code key, you know, and you see here the assembly language, and then the end code or jump, and another one for emit and CR. And we have all the sources in Force, so this was amazing. Another important feature of Force. Force is not an interpreter, and Force is not a compiler. We see here Force sits in the middle of both ways to talk to a computer. In an interpreter, you take a single line of code at a time, and in a compiler, you compile the whole program all in one pass. So there are benefits from both sides, depending on what you want to do. But Force has both. Force has the advantages of the interpreter and the advantages of the compiler. The advantage of the compiler, of course, is the speed. You have a very fast code. And the advantage of the interpreter is the interactivity. This is the basic. But here is a list of many examples, no other languages which are interpretative, like Python today, PHP, Ruby, etc. And here you see the compiler languages we already know: C, C++, Java, etc. No, Force is very simple. Force is very simple. It's we will talk a little bit more about that. So, but what is a CNC made of? A CNC basically is a human-machine interface. You see here a computer. In my case, I used RS-232 to communicate to satellite, to mini computers, which controlled servo motors and which controlled other kind of equipment, like variable frequency drives for the spindles and limit switches and etc. So I had a star system which was commanded by this Force 32-bit system, but also these small controllers had also Force. I used the C8 microcontroller for this, and in the future I went to other languages also to other micros. So you see, this is the group of the panel of a machine. This is the command, the CNC. Well, this is one of the parts also of the CNC were machined by my machine, by the CNC. This is a microprocessor. Here you see 4 megahertz controller. This was for spindle control or for automatic tool changer. And there were many of them inside the machine. What happens in the middle of the 80s when I started with this technology? There were, of course, large CNC drilling machines in the printed circuit board manufacturing, but they were extremely expensive. No one of the small printed circuit board companies could afford such a machine. Such a machine, for example, was for a very high production. And in this case, you see 1, 2, 3, 4, 5, 6. It was common to have up to 8 spindles in one machine, and they drill it very fast and for large productions. What happens with the small guys? They have no chance to buy such a machine of $1 million, $500,000, depending on the country you lived and depending on the technology. These were very expensive machines. So I found printed circuit boards were made by small companies like Primitives. These were poor PCB. Look, they are drilling by hand. This is total nonsense for the time. If you drill 1,000, 2,000 drills by hand, you will see this is a complete madness. But this was the state of art in that time. So I had the chance to bring my prototype machine to more companies and start my business. This was the CNC, and this was the beginning of the CAD and CAM. I will explain what CAM means. AutoCAD in that time brought the CAD CAD to the masses. CAD-CAM was born. CAM means machining, CAD means design. So you was using the computer to help you design computer aid design. And now you could also use the computer, this information, for manufacturing. So this was a computer aid manufacturing. This is roughly one of my programs. I had a line of different programs. This was made with LMY Force. This was a 32-bit application. And here you see the traces, the roots. All was done absolutely automatically. You had different files, file interfaces for that. This was the CNC outcome for drilling. This was different plotter languages. This is the Gerber for PCB. Epsilon is also a drilling format. So we have an interface. We could import information from CADs and manufacture CAM. We could drill with this information. This software evolved during the years, and I had the chance to contact other manufacturers like this one. This is a large one from truck manufacturing. And we developed special applications thanks to the flexibility of force. Here you see a milling machine was able to engrave these plates, these identification plates for trucks. And all the information was filled automatically by Ethernet. French manufacturer of this kind of engravings machine was not able to comply to the extremely, this was a very, very sophisticated application because it was fully automatic. Another of my customers wanted to design molds for shoes. This was Adidas at that time. And I entered also this business of mold making with our machines. Here you see some uses today. We make my customers makes different machining of high precision. You see here on this is a wheel or some industrial part. Here you see an engraving, a very detailed engraving in steel, of course, and here a stamp of a key. And well, this is one of the machines we produced and we still produce today. This is a very large machine for models, sorry, not for molds, for models. And here you see a rifle being manufactured with one of those machines. Basically, these large machines are used for aerospace and truck and cars, etc. Here you see a vertical machining center of my company also, making an aerospace part. This is for a landing gear for Liebherr, a German company. And the machine is here only making the engravings of the parts, marking the parts, but is able to do it with a fourth axis or rotating with a rotating device. This is in Peru. This is a customer of us with a 5-axis machine. He makes molds for car parts. And you see he has 2 machines. Many of our customers buy many machines during the years. They expand their production. Another view of a large machine. This was used by truck and agricultural machining of models. But oh, okay. I want to show you some machines running now. Let me see where are the videos. This was a DOS HMY, and you see the force here. This was copied from AutoCAD. This is the part of we control the software, the menu. And here you see the software was capturing. I first uploaded the software, the diagrams from the CAD, and now I am capturing the drills of this printed circuit board. These are the pads. This is called the pads. Now, this is a simulation. You have here the time and the drills the machine is actually doing. So you see, this is a C8. This is also a C8 board, Eurocard. I had a bit of problem because this is a DOS box. And you see a DOS box and Windows today has a lot of problems with direct access of video. The software access had a direct access of video. But behind this software, we have a full force. And customers in the beginning used this force to program the machines by hand. Before this CAD-CAM interface, we had a text-based interface, and customers of us used force. For example, Siemens, ABB, and large manufacturers of printed circuit boards and electronics used these machines for their inside their factories, and they used force for programming the drills and other machinings of Here you see a block editor. We were talking this weeks ago about block editors. This is part of this. The software is composed of 10 of these files, so it's a very large system. We developed this over 15 years, during 15 years. So it was a work with customers asking us different. We adapted this software for their needs. So the software grow and grow and grow over the years. And it became a very large system. You see here, for example, this is the Exelon interface. So each of these languages, of these CNC languages, has his own interface, his own language, and we adapted these interfaces to our force. We had DXE, DXF, we had CATIA, we had a lot of different file interfaces. Here you have another video I want to show you. So here you see my DOS box. I had ready a video because it was easier to show, but here is a customer. You will see in atomic energy. This is an atomic energy they are cutting here radioactive material. Of course, this is protected cell. This is called a cell. And they operate this remotely, cutting these iron rods. This is special rods inside the reactors, no? Zirconium, for example, and these exotic materials. This is another customer of us for drilling applications. This is drilling gas manufacturer tubes. These are long tubes. You need to have a special you see how smooth the machine moves because this is a round surface in steel. This customer is in Argentina. It's a large company, but their technology is from Italy. They are representatives from an Italian company. This is a German company in Brazil. They cut electricity panels and small cases for electricity. This is emergency buttons cases. And this is a large machine of 3 meters by 1.5 meters wide. It has 2 stations. You have one station in the front and the other station behind. So you can have 2 operators in the machine. Now you see he's uploading the machine from the other side and the machine continues working. So these are professional machines for production and they work all the year around, producing a lot of parts. Here you see another short video. Cutting aluminum. But essentially, this was to show you what we can do with this kind of controllers and this kind of machines. And building a perfect CNC is for me an art. I see this as an art it's not only give the coordinates to the machine. There are a lot of internal factors you need to have present. Positioning is not easy. Machine, you see here, this is the ideal trajectory, and this is the trajectory you will get if your machine is not perfectly balanced, aligned, and controlled. You have a very irregular trajectory here, and you see the dampening curves of the motors. This is not this is not for beginners. You need a lot of experience here. And you see, I wrote here, for every action, there is an equal and opposite reaction. When we accelerate a body and in a closed loop gain system, we have a result of that, and we have these problems. Now we have these irregular trajectories. You don't want to have this in your parts. Your parts will get of very bad quality. You cannot use this bad manufactured parts. And here you see the PID setup. Many people know that this is a proportional gain, the integrator and the derivative, and you need to adjust everything. And this is where force was very useful for me, to have this interaction with the machines. So this is the end of my presentation. And the goal of my presentation was to talk about what you can dream to make with force. So I thank you very much, everybody. And I continue the meeting with next participants.
Thank you very much, Peter. Great. I was always wondering what you did with force, and now I know. CNC machines. I always have a lot of respect for CNC machines if they work, and so great to see that they can be tamed with force.
Fantastic.
Thank you very much. Are there any questions to Peter?
Christian will give it a try.
Sure.
What's the advantage of Ford compared to Mach 4?
Sorry, Christian, to compare to what?
Mach 4? Did
What
you
is
use MACH4? It's a...
No. Mach is a software, it's a controller, no?
Yeah.
Well, today many people use that. This was not available in the 85. I was a pioneer in this area. There was no Mach in that time.
Okay. So that answers my question. Thank you.
Okay.
Are there additional questions?
I also worked in the CNC field back in the late 70s and 80s, and it's an incredibly interesting field. And like Peter brought out, controlling a machine, a huge machine, to move in a very accurate path without having errors is a very difficult thing. So the job was very fulfilling, and we also use some force in our machines to control certain aspects, and I miss that.
Cecil, in these times when I started with this, there was not a CAD/CAM. No, we as I talked, we had many customers in the drilling area for printed circuit boards received a force from us, and they programmed the machines with force. So using loops and using if-then and etc. And they were able to program contours for cutting and drilling in 2 dimensions. And force was fantastic for that because it was an open system, no? and also answering to Christian's question. And then we evolved. This took many years that for us to get into smooth trajectories for machining these complex parts I show you in the last pictures. It took us many years, 6-7 years, I think.
Did any of your machines also like install components onto circuit boards, or is that a different business?
Well, we sold, my beginnings was with automation and laboratory work in physics and then automation. So I was all the time connected and contacted by people doing automation. And one of our customers bought from us a CNC machine. We did a very simple machine of aluminum, and he inserted all these SMD feeders, and he inserted in spite of the drilling motor, he inserted the vacuum pick and place systems. No, so he made a machine with our software and also with force inside, and he made a pick and place machine for SMD components.
You would think today this is still a bit, I mean, so much more with the advancement of robots and robotic manufacturing. This is, I imagine this is still a very important, and I always wondered, who makes the machines that build the things that we use every day? And you're a part of that.
I will tell you a bit something. I like to make jokes. You know me. I like to make all the time something that people laugh and so. And tell you a silly joke about CNC. When I began with CNC, I was a doctor. When I entered into a company like Adidas or Siemens or ABB or some robotic company, they put a red carpet in my front and entered Peter Force into that company. I was a doctor. I was the man. I was the man. When I enter today in a company and I say, I work with CNC, they give me they send me to sweep the floor because everybody knows CNC today. This is absolute crazy. If you enter a company and you say you are a lawyer, they will respect you. But if you say you work with CNC, they send you to sweep the floor. But this is real. This is absolute crazy because CNC is everywhere. Every kid has today CNC, a 3D printer. He has a small machine at home. He makes even with wood. There are machines made with wood for CNC. So CNC is completely normal for today. But in that time, it was, oh my God, this was something out of space technology, no?
I'd like to make a comment on this. So at work, basically the mechanical engineers will design something in CAD, they export it, and they wind up creating an STL file, which, is a huge file that has all the different points in the thing that they're going to make. And then they convert that into G codes that runs a 3D printer. G codes are really primitive. It's and Peter, you by using Forth, you made a programmable language that ran a CNC computer at a much higher level than today. Today, they're using G codes. I'm trying to get my company from using G codes because we're building robots that are going to build stuff in space, and we're going to be sending these files up to build something in space. These G codes can be they can be like 250 meg in size. I'm not kidding you. So it's funny because, back in the 80s, companies like yours that use Forth actually was higher technology and easier to do than it is today. It's a paradox.
Don, when I started with these engineers from these large companies like Siemens, like Adidas, etc., these large companies, even these atomic companies. Imagine these are high level technicians. We sold machines to Samsung, to Philips, to etc., to Ford, Renault. All these these companies, no? And imagine these people, these are very, very high skill engineers, no? And they came to see this and said, wow, man, what are you doing? They could not believe, they loved to see force, they loved. So it's a pity for me to don't see this in other fields, no? Especially in robotics.
All right. So
just can I make one quick comment? I posted in the chat there that back in 2002, I worked on a project called ACE, abrasive cutting equipment, with Stephen Peltz of MPE, and it was one of my favorite projects ever. And it was controlling this car engine powered high pressure water jet to cut holes in 1,000-pound bombs, and it was amazing fun. And at the end of it, we had to show it operating to Army, Navy, and RAF personnel and health and safety officers or some such, and it wasn't really working 100%. So we actually trained one of the Army colonels, I think, to use force, because there was a terminal attached, and so we could tweak it at the end. So this chunk of steel actually dropped off because it wasn't quite perfected at that time. Anyway, just wanted to say these big machines cutting heavy objects in half is really fun. So I can understand that. And like somebody just said, the power of doing it in a fourth interpreter and to be able to recompile your script or a program on the fly is immense, much more effective than all these drag and drop GUI based things. So it always was good, and it still is good. So, okay.
Fantastic.
Yes, and Peter, I was thinking too, just when we're testing things, we're still developing it. Things go really wrong. So how did it go for you? What did you got a couple of short stories there? Tell us.
When testing went bad with machines, you mean?
Oh,
it's terrible. It's terrible. It's terrible. You drill the desk of the machine. You drill where your support is. You can break the machine in pieces. You can break mills, very, very heavy mills. It's dramatic. It's dramatic. It's not fun. Yes. I was never injured. But one time I was showing a machine to a customer, and it was drilling only, and the drill broke apart, and with these high speeds of 60,000 RPMs, 50,000 RPMs, the drill went into it injured me very, very, not heavy. It was not a heavy injury, but it's dramatic. It's not nice to have an accident with the machine.
Yeah. No, I have a scar from the ACE project. I can show it to you. I don't know if you can see it here.
Oh,
just a little. It's very faint now, but and that came about from a hot air gun, where I was trying to repair a cable that had been pulled off because it was made too short, and the movement on the axis, the cable wasn't long enough, so I just pulled it off. And I was trying to fix this in the snow outside, and I was finishing off with a bit of heat shrink tubing over the join, and I was using the hot air gun, and my hands were so cold I didn't notice that I burnt myself until afterwards. Then it hurt, but anyway, yeah, happy days, like I said in the text.
We have a lot of presenters following us. Ulrich, do you want to?
Yeah, if only I would know who is next on the schedule.
Well, we have Bill Ragsdale, we have Dr. Ting, we have Ashley Feniello.
Okay, great. Yeah. So then next in the official schedule that we published is Dr. Ting. So I would like to ask you to give your presentation, and it's a follow-up on Java Force and a very interesting system. So Dr. Ting, are you prepared to give your talk?
If not, Bill Ragsdale can continue. If Dr. Ting is not, oh, Dr. Ting is not there.
No, he's there. He's muted. I see him.
You are muted, Dr. Ting.
Aha, here we go. So you have to unmute. Yeah, okay. Here we go. Yeah.
All right, okay.
And we see your slides.
I'll do the show. Okay, I promised to talk about Java Force, but things came up very fast. So instead of, I've already talked about Java Force in the FIG meeting. So I thought I would just go ahead and report to you the newest object-oriented project, which is the CE Force 403. And I will put the link to the Java presentation on the chat, okay? So if you are interested in the Java, you can go download the Java eForce. But this morning I will talk about the C++. Okay, CE Force. CE Force was eForce written in C, and the earlier version, CE Force 21, was written in CCP and run on Cygwin. And that implementation has the Force dictionary compiled by vForce outside of the C compiler. And then in 2017, CE Force was upgraded to run on Visual Studio. And in this implementation, I had a meta compiler written in C, which will build the Force dictionary in runtime. And that one was used in ESP32 eForce. Okay, now this CE Force 403, it was written as a C++ console application in Visual Studio 2019 community. And it runs in a console window like an old-fashioned Force program in a DOS terminal. But you know, the CE Force 33 was vanilla C. And this CE Force 403 is a C++, a true C++ object-oriented implementation done mostly by Cho Chen Lee. And in this presentation, I just give you a few slides which shows the IDE Visual Studio project. And then I built the CE Force as a console project, and it can boot into kind of a DOS window. And I'll show you the words numbers, error exceptions, and then the lesson 403, which is the basically a tutorial. And lastly, I'll show the calendar as an application. So here is the Visual Studio 2019 community, and that's the IDE. And in the main window, you see the code, the C++ code. And it's object-oriented, and it makes lots of use of the list structure in C++. And TrueChain implement fourth list as an extension of the regular vector in C++. And he put in lots of features in the list so that we can implement stacks, dictionary, fourth word, fourth objects, and also object lists in fourth high-level colon words. And this one you have to compile it, and that's what it built. You built the project, and this screen shows the result of the build. And basically, this is the CE4 403.cpp file. It was compiled and rebuilt all, and it was successful. So we got the C++ program compiled. And if you push the button which says the debug without, let me see, run without debug, okay? And you get the screen. And this screen signs up saying CE4 4.03. So the CE4 is running, and CE4 is object-oriented. So all fourth words are basically objects. And here, if you type words, and you get a list of all the fourth words implement in the dictionary. And these are all primitive words. They're all written in C++, just like assembly, okay? And we have up to 0, which is dupe, up to boot, which has a token of 99. So this implementation, we have 100 words. It's a very simple, very vanilla type of fourth, but it works just like a regular E4, but it's implemented very small. It's a very small system. We only have 100 words, and the source code is about 400 lines. And then after it executes a word, it will report the stack. And the stack, and if you type a sequence of 1, 2, 3, 4, 5, and all the words are pushed onto the stack, and the stack picture is shown. And this is an implementation where we cache the top of stack in a top register. So you see here, 1, 2, 3, 4, 5 are on the stack, and -1 was first initialized into the top of stack. So you always have this -1 on the stack. And if you don't have this -1 on the stack, you're in trouble. Okay, here is how to clear the stack. The easiest way to clear the stack is type in some gibberish, and then the fourth interpreter couldn't understand what you mean, and shoots back a question mark, and then it clears the stack with only the top of stack initialized as a -1. Okay, here is the lessons file. In all my E4 system, I include a lessons file. And this lessons file has 17 lessons or more, just to show how you use this E4 system. And E4 system is slightly different from NC4 because lots of NC4 words, required words are not implemented here. But it is a self-sufficient system that you can use it to do lots of things. As the example, the lessons would show. Okay, what you do with the lessons is you open it in a text file editor. You select all the text and then copy and paste into the this fourth window, and it would compile all the words in all the lessons. Okay, and here you see the last part of the results of the compilation. The last word defined as a greet. Okay, and it compiles satisfactorily. You can scroll back this window, this console window, to see all the results generated by all the files, all the lessons. Okay, this, if I can just scroll back into one of the very interesting application, which is the calendar program. And at the end of this calendar program, it executes 2021 May, and it generates the calendar of May 2021. And this is not a trivial task, and it is a little bit involved, and it exercises lots of stack operation, math operation, input and output in words. And when I'm developing the CE4, this is the last application which I got to run correctly. Okay, there's lots of things has to be fixed before this thing prints out correctly. Okay, this is the all the words that's being compiled in the system. If you type in words, the first word in the system is a dupe, and the last one in the last primitive is boot with a token 99, and the rest of the words up to greet, which is 225. So all the 17 lessons compiled about 150 words. And I show you the calendar of May 2021. Why not show the calendar of this month? So I type in 2021 August, and I got the calendar of August. And we are at the 14th of Saturday. So this thing worked, and I'm very happy with that. Okay, the fourth implementation in this CE4, basically, it has an auto interpreter A fourth virtual machine has an auto interpreter to evaluate word list in text strings, or we call it a text interpreter. And we have also an inner interpreter to evaluate compiled word list. So all colon words, the primitives, we implement all 100 words in primitives, all 100 primitive words in C++ code. And all the words that you compile are colon words. And we need an inner interpreter to interpret all the colon words. And of course, we need a return stack to execute nested word list. And we need a data stack to pass parameters among the words. And we need a serial I/O device. And in here, it is the console window of C++. So the eForce virtual machine can be programmed very efficiently in object-oriented languages. And so far, I have done 3 systems. A JE4 in JavaScript and a Java4 as OOE4. And now there's a CE4 in C++. And they are all, we all take advantage of the object-oriented features to build the lists and all the structures that we need. All 4 words are objects. So we have primitive words, we have outer interpreter and inner interpreters can all be written very elegantly in JavaScript, in Java, or in C++. So these 3 systems, they are very tight, very small. And I think most of them has 400 lines of more or less code. And so I say that CE4, JE4, and OOE4, they are poetry. Very beautiful. And the goal of CE4 was really to replace the eForce running in ESPChain, which I did a number of years ago. After I did all this object-oriented forth, looking back into the ESP32 eForce, I felt embarrassed. It was terrible, okay? And it has to be upgraded. So Chu Chen has already ported eForce 403 to ESP8266. That kit he had in hand. He's buying a ESP32 kit, so he will move it to ESP32 shortly. We hope a simpler forth will encourage people to optimize ESP32 for more customized applications. So I like to tell you a story. This is the Chinese folklore. And 2 quarrelsome frogs live in a deep well. And they heatedly debated how big the sky was. With objective observations and accurate measurements, they finally agreed that the sky was circular and 5 feet in diameter. And I also have a nice picture to show you the 2 frogs arguing about the sky in the depths of a deep well. Okay, so I live in a deep well called Forth, and I look at the OOP, Object-Oriented Programming. With my Forth friends, we came up with JE-Forth 614 in JavaScript and OOE-Forth 204 in Java and CE-Forth 403 in C++. We decided OOP was round and 5 feet in diameter. Thank you. I will stop screen.
Yeah.
And take questions.
Dr. Ting, can you give us a demonstration on how the Forth words are object-oriented? I don't quite understand that.
Wait a minute. Say it again.
Can you give us a demonstration on how Forth words are object-oriented? I don't quite understand that.
Okay. I think the best way for me to explain it is to show you the source code. Okay, let me just briefly scan through the source code for you. So can you see the screen? Okay, this is the CE Forth. Okay, and the first part is a Forth list. This is the structure. So it's building all the structures, the stacks, the dictionary, and the primitive Forth words and the colon words. Okay, and then we have this a magic class called code. This is the class which has constructors which will build all the structures, all the Forth words. And there are different kind of primitive words, and all the user-defined words are colon words. And everything else beside all the primitives are colon words, including the constants, variables, array, and whatever you have, okay? So we use this, what I call the one-size-fits-all class to build all the Forth objects. And all the Forth objects are collected in a dictionary. And so this return stack is a Forth list. Data stack is also a list, and dictionary is also a list. Okay, and we have some base, and we cache the top of data stack into this register top, and IP and the WP are the where am I pointers and tracking. If you are in a nested list of colon objects, where you are, which object are you currently executing, and where you are in that particular object list. So here is the some word which you find, which allows you to search dictionary for a particular word, and many other things which you needed to construct different objects. And here is the inner interpreter. We have colon words, which is an object, and which has an object list. So this inner interpreter just go through that object list and execute every one of them in sequence. So this in the interpreter is getting very simple, very straightforward. And we have a dump, we have a C, very interesting decompiler, and the words which are written as routines in C++, but they are called by respective fourth primitive words. Okay, here is the dictionary. So code is used to construct all the primitives. And you can see the stack primitives because we cache the top of stack, all these stack operators becomes quite very simple, okay? And especially all the ALU operations and the logic comparators, they are implemented very simply in C++. And they are written similarly with Java and also with JavaScript. So all these primitives are written in the native programming language. And that was one thing which Sam Chen in Taiwan Fig showed us. So I just adopt his way of doing things and implement all the primitives in objects at the time it was JavaScript. And here is something interesting because the branch, if else then structure are implemented in a branch object. Okay, inside the branch object, you can have two different alternative paths, and they are both implemented as colon lists. Okay, and here are the loops object, and this loops object implements begin, while, repeat, begin again, begin until, all these loop structures. And then here is the cycles, which implemented the for and the next loops. Okay, so all the control structures are reduced to single objects. And so in the colon definition, we don't have anything other than objects. And in the colon definition, all the object lists are pure, simple, linear list of fourth objects. And then we have the compiler of the variable, create, and constants. And we also implement arrays, okay? And you can allocate space for different arrays. Each array is an object. And inside the object, the data field can be expanded to allocate any number of data objects. So this is a very flexible structure. And then we have to change the values of constants. And we have is to a vector, revector execution programs. And I think we all also have does to do customize the words. But I think we still have some bugs in the does, and hopefully we'll get it done sometimes this month. Okay, and the last but not least is the outer interpreter. The outer interpreter was the bulk of a full system. In E4, the bulk of the words are defined because we need them to build the outer interpreter. And here, in all these three object-oriented E4 system, the outer interpreter is implemented as a single routine, which is called from the main method. Okay, so as I said, in the slide I've claimed that this for system is very small, and it is it's written very tightly, and it is poetry. I hope this shows you basically what it is, and I will put up the link to the JE4 on the chat. Okay, and so I hope you will download it and take a look and see what we have in this in these three very interesting implementations.
Dr. Ting, if we were to take CE4 and put it in the Arduino IDE, could we just compile it for the ESP32 directly?
Yes. This was my goal for CE4 403, and Chu Chen, who was basically visualized this project, he had already compiled this CE4 on ESP8266. And he ordered an ESP32 kit, and when he gets it, he will move the CE4 onto the EP32, and then we will pass it on to you and to Peter and to the community to see if you guys want to adopt it in this group.
Are the values on the stack, are they integers, or does it support float too?
They are 32 bits, 32-bit integers so far.
Okay.
Okay, and we have not, okay, in the JE4 on JavaScript, all words are floating, okay? So if you really want to do math and do calculations, use the JE4, the JavaScript E4. But for the Java E4 and for C++ E4, we only implemented 32-bit integers.
Thank you.
Usually with Forth, you use scaled arithmetic, not floating point.
Just a moment. Let me post the link, and then I'll listen to the question. Okay, the link is up. Yeah, sorry.
Oh, Dr. Ting, I just wanted to make the point, because a lot of people ask for floating point in Forth. Why doesn't Forth implement floating point? It's because computers don't do floating point natively. Scaled arithmetic is actually better for most, at least with embedded systems. Scaled arithmetic, like pi is, anyway, yeah. So implementing floating point in Forth, it's doable. there's many people that have actually done it, made the source code that you can pull into your fourth if you want to use floating point. But when you're doing machine control and stuff like that, usually scaled arithmetic is
right. You're right. You're right. I think so. This CE fourth is strictly integer, 32 bits, but we don't intend to add the floating point to it. But in the JavaScript E4, because JavaScript, the native numbers are all floating, so fourth has to adopt. And so in that particular implementation, all fourth are floating point. All all numbers are floating numbers.
Mm-hmm. I'm just wondering, in Peter's CNC machine, when you're moving things around, you sometimes have to use the trig functions to calculate angles, and unless maybe you just assume, kind of like in COBOL, a format, you're going to have either 4 digits of, as you said, everything is an integer, but you divide it by 10,000 or whatever to get your.
Yeah. I would like to propose that we continue that discussion later in the Force Cafe, because it seems to be just a general way how to deal with numbers in Force, and that's a great topic for that. And I would say, okay, David is raising his hand. Final question to Mr.
Thank you, Ulrich.
Yeah.
Dr. Ting, thank you for the presentation, very interesting. My question is kind of why? Why are you creating a fourth within object-oriented languages which are running on virtual machines? And the reason I ask why is because my understanding, I'm no expert, but my understanding is virtual machines are usually stack-based, because by definition, they're ignorant of the underlying CPU. They don't know about the registers, so they can't optimize the use of registers. They simply assume a stack. That's absolutely true of the Java virtual machine, which was originally developed by Sun Microsystems, who were huge users of Forth. I mean, the Open Firmware initiative, which came out of Sun Microsystems, is based on Forth. I'm not 100% sure, but I've got an inkling that the first version of the Java virtual machine was actually coded in Forth. I'm not 100% sure about that. But it just seems to me you're building a fourth in an object-oriented language built on a stack machine. Built on a virtual machine which is stack-based. I just wonder, wouldn't the obvious answer be to create a virtual machine in Forth?
Yeah.
If you want the advantages of protection and so on that a virtual machine offers.
Yeah, for almost about 40 years, I was working on microcontrollers, and there's no need of floating point or anything. No need of object oriented. But lately, I was interested in moving Forth into a web enabled environment. That's our PCS now. So I wanted a Forth system which can adapt very smoothly into the modern network enabled Forth system. And that's why I did the JavaScript Forth. Okay. So the impetus is to move Forth into a form that more people have access to. If we only run Forth in microcontrollers, and you are targeting to the maker community.
Yeah.
But if we can make a very nice Forth system running smoothly on PC with the GUI, I think that would attract more people to try out this technology on your PC.
Makes sense.
Okay. Yeah. So, but basically, object-oriented environment is prevalent in the PC. And if we want to move into that area, Forth is better object-oriented.
Mm-hmm.
But I'm very happy to find out that writing Forth in object-oriented languages, it makes Forth much simpler.
Mm-hmm.
And I think much more understandable.
Mm-hmm.
And I would hope that, you know, when we used to look at Forth systems like this Forth from the Will Baden, and also the Forth, the C Forth from the
Bradley.
Bradley.
Mm-hmm.
Okay. Mitch Bradley.
Yeah.
I couldn't understand that. I couldn't
Mm-hmm.
understand their implementations. They're just too complicated.
Mm-hmm.
Okay. And I think the goal of eForth is really reduce Forth into its minimum, the smallest
Mm-hmm.
amount, so people can understand it. Okay, yeah. More people can understand it.
Yeah,
okay.
And I think you succeeded in that. So I can only encourage everyone to look at OOEForth or the JavaScript version. It's really amazing. I'm looking forward to CEForth and the C++ implementation. So it's I think it's really a very great step forward. So I would like to push us to proceed to the additional talks. So thank you very much again, Dr. Ting, presenting.
Thank you.
And a very interesting development that you take there.
Anthony is doing a question here. Anthony.
Yes, thank you. I hope you can hear me.
Yeah.
Okay, great. Dr. Ting, it was a very nice presentation. Thank you very much. And you produce a very neat Forth. And I understand that using an object programmed language, that it can be made on a PC system and can easily be adopted because programmers of these days understand the C++ and C# programming language. But apart from using it on a PC, you also told us that it will be ported to microcontrollers like the ESP32. If it is ported to a microcontroller, will it inherit parts of the C++ structure, making it less quick and less fast than when it was implemented in assembly language?
Yes, you are right. Okay, the object-oriented stuff runs only on big computers. For microcontrollers, the Forth is a Forth based on assembler will be much more appropriate. But ESP32 is quite different. ESP32 is almost a mainframe. And the native language of ESP32, especially on the Arduino IDE, is strictly C-based. So moving into ESP32, we have to do it in C. And now I was worried that the C++ cannot get compiled on ESP32. But apparently Chu Chen, who's doing the job, was able to port it to ESP8266. He told me that there are fewer features in C++. Some more advanced features in C++ cannot be compiled on the Arduino ESP32 C++ compiler. So he was able to trim these things off and get the things running on ESP32. So ESP32 got enough RAM, got enough flash, and got the two 32-bit processors in it. And there's no, I just couldn't find a way to write assembly, write forth in assembly for it. But our purpose is to use ESP32 for real applications. And for real applications, we have to call the very rich libraries already in the ESP32 system. For example, Wi-Fi. I just couldn't write a Wi-Fi system in Forth, but it's already in the ESP32. Why not use it? By using it, you have to write the Forth either in C or now in C++. Okay?
And if you think about it, that's actually not a bad thing. C compilers have gotten very efficient at optimizing code. So if writing something in assembly is a major pain in the neck, it would be unwise to spend time on it, but rather write an interface module in C that on the outside conforms to what Forth wants to see. On the inside, it deals with how to pass what Forth pushes in to the stack, invokes a function of the underlying OS or library or whatever, takes the result, massages the result that Forth can live with it, hand it off to Forth, and be done with the whole ordeal. That way, you can concentrate on the Forth end of things and get your projects completed in realistic time, instead of trying to beat a rather somewhat unreadable machine interface over the head to gain a minimal advantage in assembly.
Yes. Yes, I think I have to remind you that Will Baden, who wrote this Forth in C, and he always maintained that the C is a high-level assembly, high-level universal assembly, okay? So we have to take advantage of that. So when you are thinking assembly, thinking it's advantage to think C as assembly, but it's universal. So you have the advantage in C. Once you write a Forth in C, you can carry it to almost to anywhere. And I really appreciate that feature. Thank you. Any more comment, or are we taking a break?
Yeah, I had a question regarding you said you also worked on a JavaScript Forth.
Yes, yes.
Yeah, so I've been working on one the last few weeks, a little bit. It's about 300 or 400 lines of code, and it integrates with a web browser. I just did that today. So you can generate DOM objects from the Forth, and it gets played up in the web browser. But I don't know if that's your direction where you're taking the JavaScript Forth. I didn't find it being part of your zip file, so maybe you could say something about it.
JavaScript eForce was done a couple months ago. So if you scroll back our presentations, and you'll find a link to the JEForce assistance that we have already put up. Okay, and it is you are right. The source code, the source code of JEForce is about 300 lines. So you can.
Well, it's JavaScript. This is JavaScript, right? It's not Java. It's JavaScript.
Yeah, JavaScript. Mm-hmm.
Yeah. Okay. Does it integrate with the browser or run as a web server, or doesn't have those things?
The JavaScript implementation is interesting in that you got two files, HTML file, which defines the user interface, and the JS file, which runs forth. Okay.
Right.
So you just click the HTML file, and you got the window opened up on your PC. So it's
okay.
a very pleasant one. Mm-hmm.
Can it manipulate the DOM objects, or it doesn't do that yet?
Beg your pardon?
Does it manipulate the DOM objects, the objects in the browser?
No, it does not reveal objects. So all four words are objects, but you cannot create objects or use the inheritance or any of the object-oriented features. But I think each fourth word is an object, and that's much more powerful than any other object-oriented programming techniques.
Yeah, well, it's similar to what I've done then, because my word definitions list is basically just an array of the definitions of a code, right? So the interpreter loop is simple, but I have an integration with the DOM model, so you can actually manipulate and create and append stuff to the JavaScript. So basically, you can modify the UI of a browser, so you don't have to use JavaScript for it. You should be able to do it from the forth.
I see. Yeah.
But it has a lot of similarities with the object orientation forth. Yeah.
That's great.
All right. Cool. Great.
Perhaps you could present that at a future meeting. I'd like to see that.
Yeah. Peter asked me if I wanted to do it today. I wasn't sure if he wanted me, but it's not complete yet. So I would like to go forward with more functions. You can define functions in it, but I don't have any control structures yet. So that's where it's at. All right. Thank you.
Right. We're looking forward to it. So thank you very much. And thanks, Dr. Ting. And I would say let's proceed. Our next speaker then will be Bill Ragsdale, and he's doing infinite loops, program test, and so on. Bill, are you ready to present? Yeah.
We are ready.
Go ahead. Sorry.
We are ready.
That. Yeah.
Thank you very much. Thank you. The topic today is going to be fairly short, and I suggest you have paper and pencil handy, because I'm going to show 2 lines of code that you might want to jot down or make a screen capture of it. The material will be posted, but I think it'll be quite informative if you jot down the 2 lines of code when they come along. I'll point it out. So this is program methodology. In Forth, we code and test incrementally. We code, then we do some testing, a couple of new words, design, test again. We go through a cycle of code, compile, test, encode, compile, test. However, we don't necessarily need to have the testing available all the time. It would be nice to have the testing only when we make major changes, and then we can reactivate our testing. So the idea is when the code is completed, the tests may be repeated, but only repeated from one point forward. In other words, instead of testing everything, maybe you just want to test the last 2 or 3 components. So historically, we've had the use of the high-level words if, else, then, the bracketed if, else, then. These are interpreted at the source code level, whereas, of course, we know the regular if, then, else is at the compile level. So I'd like to build on that. The way this operates, of course, is that the bracket if takes a Boolean flag. If that flag is non-zero true, we execute or compile the text following until else, then jump to then. If, however, it's 0 or false, we execute or compile the false code. So this is selective. You can selectively choose, do you want to execute the code after the if or after the else? And as a note, the bracket if is an immediate word. It actually contains a little mini interpreter that looks for else or then. And so if can be embedded in colon definitions or in source text, and it will allow, again, selective interpretation or selective compilation. So how can we actively select test sequences? Here is the screen. I would suggest you screen copy or you write down. There's only two lines that are important. First is that we declare a value called test limit. In this case, it's set to 7, but the test limit is going to determine the range of testing that you execute. And then the word that I call star if. Star if takes a number, a test number off the stack, and it compares it to test limit. And if the result is true, then it will execute paren if. So this is a selective way to execute the if based on an input number, and the input number is our test number. So if when you encounter an if, it's going to accept that number and it compares to the limit, equal or greater to, interpretation continues to X. Otherwise, it just skips to the then and no tests are completed. Here's the D chart for it. We simply have the top left a code module. After the code module, we give it a test number, and then if that test number is equal to or greater than our test limit number, then the code sequence, test code, and report will be executed. Otherwise, the test sequence is jumped and we go to then. So here's a typical example of a test. This is test number 8. So you see at the top left, 8 going to star if. If our test limit is set to 8 or less, then the following code will execute. The dot paren gives us a little reminder. It says this is test 8, and it's a test of, in this case, the word subrandom. The next two lines take a matrix. The A bracket is a matrix. A random number is generated, and the matrix is filled with random numbers, and then the A bracket lists that. So this is a simple way. We're testing the word subrandom. We give it some test conditions, and then we list the result. Again, selectively, we may or may not execute that. If it executes, the output is going to show us the 8 test of subrandom. Remember, that's in the little dot bracket sequence. That's a reminder of what the test is. And then the listing of the matrix content with random numbers. It can be a little more complicated than that. We can have a code module with our selected star if, and then inside that, we can then have additional tests that are made in the usual fashion for if, else, then. So in this case, this allows, say, multiple testing sequences, which we'll show right here. Here's a test sequence, test number 4, and it's testing plus minus divide. We come up with a series of numbers, 100, 500 plus, 200, minus 4, divide, and we expect to get the number 100. So at the end of that line, we say 100 equal. This is testing to see, did we get the expected result? If we did and it's true, then the bracket if will execute, and it'll give us a little report that says got the expected 100. If, however, the math is wrong, the numbers are wrong, or our setup is wrong, we'll get a little message that says error in math operators. And then you see the 4 bells there. I like to include that. The bell is the ASCII 7 character. And by ringing the bell 4 times, it's an alert. It says test number 4 failed. And it's a little wake up call to say, better stop and see what went wrong. So in this case, it works properly. We're getting the little confirmation message number 4, and the fact it's testing plus minus and divide, and then we get the message, we got the expected 100, interpretation compilation continues. And the alternate would be if the test fails, you get the failure message and then the ding, 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 which is the bell rings 4 times. Here's one that's just a little more comprehensive. This is test number 7, and it's testing the literal filling of matrices under 2 conditions. The first section of code takes a matrix A and fills it with literal values and lists it. The A lists the literal values. To test if this process can be compiled, that entire sequence is created as a colon definition, and then again it's tested. The second line from the bottom says that A is filled with zeros. Then we use the fill command to fill it with those integers, and then we list it. And finally, at the end, we forget A. So that whole sequence is rather involved, but this is what we see on execution. It shows us the test number 8. What it's doing, it shows us the first sequence filled with integers and the second sequence. So again, there's no interruption. As long as everything goes fine, it will execute right from top to bottom. Here's a live example. This is about a 1,000-line program on matrices, and I carry all of the test programs for all of the components in this matrix language. So there's about 1,000 lines of code, and you see the tests are there. We'll go backwards and take a look at them briefly. Now again, I don't run all the tests all the times, but whenever a major change is made down at the bottom structure, simply I can change one number on that test limit sequence, and I can recover all of the tests. Here's a comparison with and without the full testing. If I do a fload of the file, which is this matrix 2 file, if the testing is fully performed, the recompilation takes 5.5 seconds. On the other hand, if I reload with no testing, then it takes 26 milliseconds. And very often I've got the testing set about 3/4 the way through, so that it may take maybe 1 or 2 seconds extra to do all the testing. So why are we doing this? Well, the first is that you're thinking most clearly about the code just as you have written it. And very often I write the test sequence before the code, so that becomes an objective in the structure of the code is to match the test sequence. So while you're writing the code, think about writing the test methods before or after. You're able to preserve those methods in the source code. A lot of times, if I'm typing a test from the console, I type it and it's gone. This way, most of my testing is done inside the source code. And then again, the test routines are only reused when they're needed. I'd like to credit other people who've done testing. Ulrich has a paper at Euroforth 2019 on testing. The Forth 2020X has a test suite, and it gives a testing method that is very straightforward and very simple, one-line processes. And finally, on GitHub, a programmer named Ending has a simple test. I'd like to thank Andrew McEwen and Tom Zimmer again for creating Win32 Forth. This is a gold mine of resources. And also, I'd like to thank the European team who updated it in the early 1920s. This material can be found at my GitHub site, Bill Ragsdale, under Forth Projects, and this is Program and Test. And then I have written a 90-page guide to Win32 Forth, which is also on the same site. I will copy these over into the comments, so any people want to visit that code, it's available. And so back to Mission Control. Thanks for your help and your attention.
Right. Thank you very much.
Fantastic. Excellent.
So, do we have questions to Bill?
Not a question, but I just want to show Bill.
Yeah, Scientific Forth.
Yeah, I got a copy of the Scientific Forth. Okay.
That is gold mine. They sell on eBay for $125.
Wow. Yeah, great.
You're very fortunate. And the work I've done is derived very directly from that book. And probably in a month or two, I'll give another talk on data structures, two-dimensional data structures. But that book is a gold mine. However, it is very dated. Unfortunately, it has extensive work on memory management, which is no longer necessary. And it has a very powerful but complex way of typing math operators. So anyway, but it's a gold mine of knowledge. Good, thank you.
Yeah, this one, I found in a box that Al Mitchell left us. Okay. Yeah, he left lots of books in this book, in this box. And I just, a couple of days ago, in my garage, I said, well, what is this box? I opened it up and found this one.
Yeah, great.
On the other hand, on GitHub, a PDF of it is available because there is a team on GitHub who has been trying to reconstruct that book. With the permission of Noble's widow, they are reconstructing that book chapter by chapter. But the process has been in process now for 4 to 5 years, and I'm not sure if an end is in sight.
Right. Are there any other remarks or questions to Bill? Doesn't seem to be the case. So thank you very much again. I appreciate that, of course, because I intersperse tests and programs a long time, selectively doing the tests. That's a good new idea. So I really appreciate that. So wonderful. And so let's see.
We have Ashley.
We have Ashley. So we're missing the GA 144 development report, but we still get something about the course. F18.
Yes.
Ashley will talk about F18, which is the core of the larger chip. So Ashley, are you ready?
Yeah, I'm ready. Yeah, so I'm Ashley Finello. I'm just going to present an old project of mine. It's from like 8 years ago. When I was first learning about the green array architecture and first getting my head around ColorForth and whatnot, I made this little system basically to learn. And it's probably useful to others who would like to learn as well. I have this pre-recorded, so I'm just going to start the video and then I'll be here afterward for questions. This is a presentation of an old project of mine. It's a simulator, debugger, ColorForth editor, and assembler. Let us play with the F18 computer. So the F18 is just one of the cores in the Green Array's 144 core chip, the GA144. Very interesting chip. I just wanted to play with programming just one of them. The documentation on their site is pretty good. It's just 2 pages, very compact, it explains the entire machine. I was most interested in this little instruction set. 32 instructions, very minimal. Very Forth-like names and semantics, and I just wanted to play with it. Each core has 120 words of memory. They're 18-bit. It has 2 stacks, a data stack, and the top of that is this second and top register, and a return stack with a R register above that. Then a couple of general purpose registers, A and B, and a program counter that fetches instruction words into this I register, the instruction register, where they're executed. You can see that they're packed into slots there. So this is the project at GitHub, Ashley F. Color, and down below are some links to some blog posts going into some of the details about this wild, interesting machine and some of the inspiration for creating the project. So in 2013, I went to Strange Loop in St. Louis, and Chuck Moore showed up and talked about the Green Array chip. There's the instruction set there up on the screen behind him. And I thought it was so cool, so interesting. I bought the eval board and played with it. But I'm more of a software guy, and I really just wanted to play with the instruction set, and I wanted to write this blog series and let other people play with it also without needing hardware. So I made this thing. It's a ColorForth editor, an assembler, and these all work with block files and a machine that executes the assembled code. It's all written in F#, which is a nice functional .NET language. You don't need to know that language though to use the system, but here's an example of some of it. This is the definition of the machine. Just these 32 instructions, the entire machine implemented in 81 lines of code. Very simple. So once you've synced and built the project, you'll see in the bin directory separate executables for the editor, assembler, and machine. What I like to do is run tmux and just run the assembler over in one pane and run the editor in the other. And what happens is as you save things in the editor, the assembler automatically picks them up and assembles them. So you really need a special editor for Colorforth because the tokens aren't just syntax highlighting. They're actually colors chosen by the editor at author time, and they drive the semantics. So this is an app that has a bouncing ball on the screen. So then we have its position and direction and color, and it can move and bounce off the edges and be drawn. So red words are the definitions, white words are comments, and they can be toggled on and off like this. Green words are for literals or calls to previously defined words. And gray words are F18 instructions. So that's something special about this editor for the F18. Yellow words are macros that get expanded at assembly time. Then there's also blue words that are for formatting. So this is really just a flat sequence of tokens, but the formatting words give carriage returns and tabs and things to make it look nice. When a block file is saved, the assembler automatically picks that up and assembles it. So you can see that on the right hand side. Here's some of the correspondences. So we have the draw word in the source on the left, and we can see that it gets assembled over here on the right to this location in memory. And you can see that the literal value there ends up becoming a fetch p, and the literal value itself is in the whole next instruction word. So that's how this works. You inline literals in with the instructions, and fetch p just fetches the program counter and increments over it. Then this call to color plus becomes a call instruction followed by the address of color plus. And the next two white words, or and store B, are F18 instructions directly, and they just go directly into slots. And the call to ball Y, again, just becomes a call instruction, and the remaining slot has the address. Then you can see yellow words like for and next end up getting expanded. So it does a fetch p of the value to put on the return stack, followed by a push that puts it on the return stack. That becomes the induction counter for the loop. And there's the 2 star, the body of the loop, and then the next expands to a micronext, which is an interesting instruction that just creates a little tiny loop inside of that single instruction word. So the assembler writes to block 0, and the machine conveniently boots up with the P-register reading from block 0. So just running it, we can see what happens. We get this ball bouncing around the console, leaving a colored trail. Nifty little demo. Alright, so let's go take a little closer look at the editor. So it's a very Vim-like editor. Block 1 has instructions. HGLK will move around. You can jump between definitions. You can set the colors of the tokens with Shift R, Y, G, W, and A. This is why we really needed a special editor to be able to edit Colorforth this way. Since W comments things out, it also advances the cursor and it makes it easy to just comment out whole lines like this. You can toggle the format words, the blue words. You might need to be able to see them so that you can edit them. And then you can also toggle comments. So this is kind of like the shadow blocks idea in ArrayForth, keeping comments and code separate. At least this way you can toggle them on and off. So I like this. Focus on just the code. And it's a block editor, so you can just press the number of the block you want to load. You can save with S, you can cut and yank with X and Y. And it just keeps a stack of what's been cut. You can go around in PPP to paste back from the stack. So even though it's just one token at a time, it's very easy to move things around this way. Then just like a normal Vim, you have normal mode for just navigating, or you can go into insert mode and enter new tokens. And while entering code, automatically the first word is red and then it switches to green unless you choose otherwise, and you can do this while in insert mode. Then also there is an infinite undo, so everything you've ever done you can just undo, and you can redo if you like. So you can be pretty fearless about editing blocks. Then you can also find the word that's under the cursor anytime and navigate around pretty easily that way. Gray word's a little bit special in the editor. It restricts you to entering only legitimate instruction names And these get saved instead of as source in the block file, they get saved as the actual instructions. This is an idea taken from Jeff Foxworthy's AHA, and also from Chuck Moore's Etherforth did this. So it'll restrict you from converting illegitimate words to gray, and it will, beep at you if you're trying to type something while in gray mode that isn't legitimate. So that's kind of an interesting feature of the editor. So let's make a little program from scratch. So we'll make something that just prints the alphabet to the console. We'll make an alphabet word, and now ASCII A -1 in hex is 60, and 26 letters in the alphabet -1 again in hex is 19. So we'll iterate through those, and for each one we'll just add 1 to the ASCII value, duplicate that to keep it, and do a store B, which B initially points to the console in this machine. So that should be about it. Basically, this will print the alphabet. And if we save that, we can see what it assembles to. So it assembles into these 7 instruction words. So alphabet is defined as starting at address 0. And these literals get inlined into separate slots, 16, 19, and the first instruction word has 2 fetch P's that fetch them. So what really happens is the program counter is pointing here, loads this into the instruction register, and begins executing those slots, which continue to increment the program counter past those literals. The for macro expands to just push that 19 onto the return stack to become the induction variable, and then execution continues. So program counter would be pointing here now, and to do another fetch P to get that 1, and then the rest of these are pure instructions, add, dupe, and store B. And then next becomes an actual call to address 3. So this is a large loop rather than a micro next loop happening within one instruction cell, which we'll see later. This is a regular loop. So it appears that this program is already in memory. It's been given addresses by the assembler, but what actually happens is this gets written to block 0, and the machine boots with the P register reading from block 0, just streaming code in one instruction word at a time and executing them. If we want it to actually end up in memory, we have to use this load macro, which inserts this little program that loads the rest of the stream into memory in the F18. So it creates this fetch P that fetches this 6, which was computed to include all of the instruction words to follow. There's 7 of them, -1, so it's 6 for the induction loop. And then this instruction word, which is part of the stream, is just a little micro next loop. So it does a fetch P and a store increment, which stores through A, which begins life pointing at memory. So this little tiny loop will just fetch through the P register off of block 0, storing into memory, do that 6 times, 7 times, and the program will be loaded. And then it follows with a call to the alphabet word to kick things off. So this load and init work together to wrap your program in this little loader that will stream it into the processor's memory and then start executing it. So now if we just go run the machine, we should be able to see it do what it's supposed to. It should print the alphabet to the console. And sure enough, it's exactly what it does. Now just to get a better idea of how the little loader works, I'm going to go back up here and insert a break instruction. So I actually have added a few instructions to the machine that aren't F18 instructions. This break will enter a debugger. So with this we'll be able to see the state of the machine and step through code. So here's the entire state of the machine. Here's all the registers, the data stack, and the return stack, and part of memory is shown to the left. So what happens to start with is it fetches through the P register from block 0 an instruction word and begins to execute it. Here it itself does a fetch P that fetches the next instruction word, still just streaming in from block 0 though, not from memory. Puts that on the data stack and then pushes that to the return stack. Then this instruction word gets fetched, and this is interesting. So this all goes into the I register and begins to be executed, and it itself is a little micro-next loop that just continues to be executed without anything in memory on the machine. Each step through the loop is going to fetch through P, one of the instruction words being streamed in, and then store through A and increment A. A begins life pointing at memory, so that ends up basically filling up memory with whatever's streaming in. It goes through that micro-next loop 7 times, until the R register decrements down to 0. And so we have the entire program loaded. And then at that point, the final instruction word there is a call to address 0 to kick things off. So you can see everything being loaded here. And then finally, we fall out of the loop and we end up doing a call to the alphabet word and executing all of the code within the alphabet in a little program that we've already walked through. It ends up printing to the console. Of course, that's getting eaten up by the debugger taking over the console here. So I really just wanted to play with the F18 instruction set and see what can be done with this ridiculously minimal set of instructions and see what kind of tricks can be played. So for example, you can duplicate the top of the stack and XOR those together to generate a 0 rather than loading a literal, save some space. There's this not instruction. The minus sign is actually a not, a one's complement not. You can generate a 2's complement negation just by adding 1 to that. There's no subtraction instruction. There's add, but there's no subtract. But using the not and add, you can generate subtraction, either by doing that and adding 1, or you can subtract the second from the top on the stack. That's kind of reversed in just 3 instructions. Or you can push and pop from the return stack and do it in 5 instructions, but in the right order. Funny enough, there's no swap instruction. There's over, which is similar, but leaves garbage behind. You can either do that and then later drop it, or because it's a circular stack, maybe just leave that forever. Or you can accomplish a proper swap in 7 instructions this way, or with a little trick, XORing twice, you can do it still in 7 instructions, but using less of the stack. Or if you're willing to stomp on register A, you can save a few nanoseconds and a couple of instructions and do it this way. So there's all these nifty little tricks you can play, and it's fun to see what's possible and try your best to optimize for speed and size. So here's a pretty nifty trick for creating variables. So first of all, of course, to create a constant, just simply define a name for a literal. But then to set that constant, we do something like this. And if we assemble it, we can see what the code actually looks like. So the constant is just a fetch p return followed by the literal. So that's pretty obvious. But to store into that variable, we do something like this. We do fetch p drop store p return. So the first fetch p will fetch the instruction word here, but then drop that. And now the p register is pointing at the value, and so the store p stores into it. So it's kind of a cool little trick to just in 3 words create a variable. And we did that actually in the ball example for all the ball position and direction and color and everything were variables defined this way. Another tricky little thing to point out is that red words just define names for addresses. And there's nothing that says that a definition has to end with a return. So for example, max can be defined this way. It's just less if swap drop. And then absolute value is basically dupe, neg, and then take the max. And you can define it in this order and just allow the abs word to fall through to the definition of max. There's also nothing that says that you can't have multiple returns in a definition. So sometimes you might have an if with an early return. So there's all these cool little tricks. It's pretty fun to play with. So have fun. So there you go. It's kind of fun to play with.
Fantastic.
Thanks.
Yeah, thank you very much.
Yeah.
Are there any questions?
I just have one quick question. The use of the word or as the for the opcode. I believe in the F18 instruction set, or is called or, but it's an XOR.
Yep.
Is that still the case? So you didn't opt to change its name?
Right, yeah. I just kept exactly the same names that the green array, array forth uses.
Yeah, it's just unfortunate.
Even though it is a little confusing.
It's okay, thanks.
Any other questions?
Oh yes, a quick question. Is this available somewhere? Could you post the link, please? Sorry.
Oh yeah, I'll put the link in the chat. Yeah.
Yeah, thanks.
It's just at GitHub Ashley F. Color. I'll put the link here.
Okay.
No.
Well, guys, I propose we go now for the coffee break. I want to explain. We had another 2 participants in the meeting, but they did not show. They did also not respond to my emails and etc. I understand this is a summertime and people are probably traveling or etc. So they are always invited for future meetings. But today we accomplished our goal of presenting a wonderful meeting. It was fantastic to see all you again. And I hope we can chat about other themes, and we have also Don Golding after the coffee break. And many of those questions we did not answer during the meeting, we can do now in the Fort Cafe. What do you think?
Yeah, sounds nice.
Okay, 15 minutes then, Ulrich?
Yeah, I would say that means 10 minutes past the next hour, whatever is the next hour at your location, which is 8 o'clock at night here, but yeah.
Oh, sorry. And also Howard wants to show us something. I don't know if Howard will show us. And also Atle, if Atle is in the meeting or probably he comes later. So we have Howard after the coffee break, Don and Atle. Okay?
Very good. Very good.
See you then.
See you in 15 minutes.
Bye.
So bye-bye all together. Have a nice weekend. Bye.
Dimitri, are you there on Don? Are you there? Atle, you are also there. Are you ready for Rolf is here also?
Peter, wärst du so nett und würdest mich ja wieder auf Facebook meine Nachrichten lesen? Also irgendwie sehe ich da keine Flagge von dir.
Okay, okay. Perfekt, Rolf. Ich war sehr beschäftigt, weißt du?
Okay, okay.
Verrückte Woche, diese Woche.
Das kannst du noch mal sagen.
So ist das. Das war Cornelius.
It was a terrible week for me. It was a terrible week for me, Rolf. We have a message from Don. He wants to present Dimitri with Prolog because Dimitri needs to go. But I will ask them to be very, Dimitri, you need to be very short in your presentation and prepare a better one for September.
That's fine. I can keep it really short. It's literally just a demo, and I don't know if Don will present immediately after or later, but yeah, I'll be happy to share my work. Sorry for interrupting you.
This is not my problem, but I was telling Don, if we don't announce these presentations, they throw away, you know, nobody, because now in the group is only 30 people left and we were 50 or 60. So you lose audience.
Yeah, the reason I wanted him to do a quick demo is it has to do with my talk. So it's important for my talk.
Yeah, I know.
Okay, just let me know when to go. Or should I go now? Yes,
Are we all back? I don't know if everybody's here, back.
I mean, it's 10 minutes past the hour and the break is over.
Okay, well, I will give a bit of an introduction. So yes, I have been working on an implementation of a Prolog in Forth. And for those who don't know, Prolog is a logic programming language. It was fairly popular in the older days of AI because it, like Lisp, it had powerful abilities to manipulate symbols. So I'll just quickly share the paper that I was working from, which is let me make it big. Compiling Prolog to Forth by Lou Odette. And I found this very interesting. I think this has been on the group for some time, and I was interested, but I don't think there was any code available on the internet. So I went ahead and tried to implement this. So this is how Prolog tends to look when it's written. It's a knowledge type language. So these are just facts, you know, that in this case are saying Isaac is male, Lot is male, Milka is female, and things like that. But you can also define other relations like X is the son of Y if Y is the parent of X and X is male. These capital letters are called logic variables, and they are what I think makes Prolog quite powerful, because a Prolog, the technical word is predicate, but I'll call it function for the sake of simplicity, does not go in just one direction where you put something in and you get something out. You can actually do the reverse as well, because all it does is it pattern matches all the inputs and make sure that they unify, that is, that they all agree with each other. So I will, actually I might give some examples, a quick example of what Prolog can do too. But what surprised me about this is that the amount of instructions you need to implement it, this is it pretty much. So you can make a virtual machine with just const, var, functor, pop. I think there's 2 others that they've left out there. And that's it. You can compile anything you write in Prolog to those. So this made me realize it was a lot simpler in some ways to implement than Lisp, but it has similar capabilities to Lisp. And this is debatable, but it's possibly more powerful. So this is one of the things that made me turn to Prolog for symbolic manipulation in AI. And I had to go through the codes listing, go to it, code listing here and type that all out manually because you cannot copy it from here and it's not available on the internet. And I had to convert it from a 16-bit fourth to make it at least compatible with 32-bit. Hopefully I've made it independent, so it'd work on any fourth now. And I also had to do some things to bring it up to the ANSI fourth standard, just because that's what is popular at the moment. So I should probably give some examples of what we can do. Would you like to see what? Yeah, I'll give another quick demo.
Sure.
There's 2. One is of just Prolog and one is the actual implementation I've done. But it might be easier to see how powerful Prolog is if I show you an example in a complete implementation. So this is an example where I've actually, somebody shared something on Facebook where you had the stack manipulation words, and you could give what you want the stack before to be in the stack after, and it would figure out what words you needed. So this is actually how you do it in Prolog, which is really interesting. You pretty much just write a fourth interpreter. So notice here, this is the starting stack. This is the stack at the end, and these are the instructions. The way I've done it is that the left side is the top of the stack. I know that's not intuitive, but it's easy to implement. And you notice that swap has swapped those 2 values round. You can also have more instructions such as swap and drop, and it's done executed that. But what's really interesting is that you can actually ask Prolog instead, okay, say I had 1 and 2, and the result after executing something was 1. What is that something that I'd have to execute? And it gives you the answer. So I consider this to be very, very powerful. And I have ideas that it could work with Triune OS at the goal level, where it's working out high-level things, it's working out paths, because this could be a what your starting point on the left, and this could be a destination on the right, and in the middle could be the steps that you need to go from one to the other. That could be like a compass heading, for example, go north and then go east, and then you'd get your destination. Meanwhile, the rest of Triune OS would cope with obstacle avoidance and things like that. So I wish I could, okay, I know what I'll do. I'll share the whole screen. It'll make it much simpler. So now I'll show you what I've actually done in fourth, if I can. Yep. So this is my implementation, and you've got some examples here. So let's run one of these tests. The first is test 1, and the predicate we are testing is append. The definition of append is up here, and basically it says if you've got an empty list and you append something to it, then you get the thing you appended to it, because an empty list is like 0. If you add something to it, then you just get the number you started with, or the list in this case. And then the next rule, if this doesn't match what your input was for your query, then you have this rule as well. It will check this rule here, which basically goes down the list and it reconstructs it so that the second list is appended to the first. I'm giving a really brief description of this because it would take a bit longer to explain fully. But it's a very declarative style. You pretty much just state, okay, this is what holds. It's not about input and output. It's just this is how X here relates to X there. You know, this is how Y here relates to Y there. So I will run this now on test 1, which has a list of Bob and Fred, and it's appending a list of containing art to it. Now, bear in mind that the representation of a list is through cons cells. So, for example, Bob and Fred is more like this in the implementation. So what you're doing is you're making cons cells. Those who are familiar with Lisp might be aware of this. Nil is the empty list, and you're adding Fred onto that, and then you're adding Bob onto that. So that's how it's represented internally, just so you're not too confused when you see the result. But this is equivalent to this. It's just a implementation detail of lists. So let's run test 1 and see what the result is. We should get a list of Bob, Fred, and Art. Okay, so now which version do I run or run? Because I have 2 versions of it. I'll try this version because it gives a nice trace. It's my debug version. So this is how I have to do it at the moment. Test 1, cool. Test is just initializes all the stacks for testing. 0 is the number of arguments that the next word takes, which is test 1, and then I call it. So there we go, it succeeded. And while I was debugging, I needed some things printed out. You can see each of the primitive words being executed and unified and stuff. And to view the results, it's not done automatically at the moment, so that's something I'd like to add. But I know that the variable is at position 24, so I can just print it like this. And we got the result we expected, because this list here is of Bob, Fred, and Art. So they were the 2 lists were successfully concatenated or appended. Now I'll give another example, which is the second test, which reverses a list. So in this case, you've got Bob, Art, and Fred. The reverse of the list should be Fred, Art, and then Bob. So let's check that that happens. This is, of course, the definitional reverse. Notice that it is quite short, really. This code is produced by a compiler, by the way, but you can learn to write it yourself. So don't worry, that's not, a human isn't expected to normally write this. You can have tools to produce that. So let's go back to 4th and try reverse, which was test 2. And just to remind you, the results we're looking for are Fred, Art, and Bob. Okay. So that one took a bit longer to run. Reverse is reverse actually calls append. So you can see it took a few steps to get to the result. But what do we have? We should have the result at the same place. Oops, yes. So let me check if it did that. Yep, you got Fred, Art, and then Bob. So this is a point now where we have a working implementation of Prolog in Forth. And I've not put this on GitHub yet, but I do intend to make this available to everyone. Currently, I think it's only working in Forth Win. It might run on some other platforms as well. But ideally, I'd like to get it to run on the ESP 32 as well, for those who might like to play on it and there. And it'll be part of the Triune OS as well, or at least the work I'm doing with Don at the moment for the processor is developing for the FPGA. Some of these, maybe the virtual machine or maybe the parts that make up the virtual machine will be implemented in hardware, or at least be micro-coded. So that's the kind of thought we'd have, and then we can easily have an integration with this. So that's all I was really going to present. I don't know if there's any immediate questions in response. I could give a longer, more detailed presentation next time.
Yes, Dimitri, we need for next time a longer presentation. You prepare everything. This is super interesting for all the group, I think.
Glad. Okay, I can do that.
Great work.
Thank you, Don.
Okay, we have now Atle and Howard Oakford. Any of you who want to talk?
I can go now if you like.
Yes, Howard, please.
Okay, I just want to show something. It's a Colorforth-ish thing. Let me share my screen. Okay, can you see my screen now? You should see. Right, Colorforth Win. It's called. It's I'm trying to escape from the restrictions in Colorforth, which uses this brilliant Huffman encoding, and this is just a simple test program that I did to try out some ideas. If I run this, what's happening here? This is a conventional SwiftForth terminal. So if I hit a character here, you can see characters appearing up on the top screen there. Okay, now this is a simple Go assembler. Hang on, if I can get rid of the. Where is it? Sorry, where's it gone? Right, so if I can explain what you're seeing here, if I type some characters here, it's just a conventional terminal, and as you type a character on the it's coming wild on me. Come back. Right, this one. Let's get rid of that. So the the screen here is an assembler program written in or using the GoASM assembler. I'm trying to move away from NASM because it's too complicated for me, and the GoASM assembler is really neat and elegant and in line with Forth and Colorforth type simplicity principles. So my problem is, how do I, if I just type some characters here, you can see as I type characters here, I had it all beautifully laid out before, but it's closed itself down. Right, okay, so as I type characters here, you'll see them appearing eventually here. Right, okay, so what you're seeing is it says 61, that's hex 61. So and so on. Now, I'm trying to firstly convert everything into 16 bits Unicode. So as you can see, I've got some Chinesey characters here. I should be able to send some characters there. And I'm also trying to encode not only the 16 bits for the characters, but also color. So if I now do this one, right. So I should be able to do something and change the color. So as you can see, right, now how this is happening is that every time you hit a character here, it actually sends 4 characters to the terminal. Because I'm trying to crack this problem, exactly how do you transfer 32 bits at a time? Because this is over a conventional COM port. So you can only send a single character. So how I'm doing it now, I'm using a Modbus type principle where you send 4 characters and then you have a short pause. And if the receiving end, if this terminal does not receive a character after, for longer than that interval, then it says, oh, I've not got anything, and it resets. So you always send in groups of 4. Simply by encoding the UTF-16 character as a pair of bytes, and then the color, and then I've also got something that I'm calling action or something similar. I'm trying to refactor the way Colorforth works. Can I just check that everyone can hear me, because my screen has gone.
Oh, we can hear you.
Good. Okay.
Yeah.
Okay. It's hard when there's no visual feedback at all and no audio feedback. I just wonder whether I'm talking into the void.
Why don't you use the delimiter?
Yes, I thought of that. I thought of using HDLC type thing where you've got a flag and an escape character, and you begin with a flag, and then if you want to send a flag, then you precede it with an escape character. This kind of thing. Yeah. Anyway, I was trying out various options. What I wanted to do was get the easiest way of doing it. If I just jump to the code for this, somewhere here. Okay. So this is process the received quad byte, and the code is actually quite straightforward on a PC, because this is on a PC. So you've got access to everything Windows gives you. So I accumulate how many bytes I've read there, but the code to handle it is all in this this page or so here, 1.5 pages. So it works pretty reliably in the sense that if you if you want to transfer a block, say 1024 32-bit values it'll be, then you can do it all in one go, and there's 0 overhead. Whereas if you were doing it with an HDLC escape character type scheme, then you'd have the overhead of all those extra characters, which could be a factor of 2 higher. If you only sent an escape or a flag character, you'd have quite a lot of overhead. Yeah. Okay. Well, that's it really. This is I'm thinking about these ideas to how to make Colorforth communicate with the rest of the world. So the first thing I wanted to work on was a simple protocol that could get from one computer to the Colorforth terminal. Encoding was simply sending 4 bytes, and then the terminal has to pick them up and then work out what it means. So just to show you what's going on here, each character, the characters in this are drawn by Windows calls from an assembler program. So I'm trying to get as close to the hardware as I can, and the hardware in this case is actually Windows 10. If I do Control A here, then you can see you've got some interesting characters and interesting colors. I presume it keeps changing every time you do it as well. So anyway, I just wanted to share with you that's what I'm currently doing with towards a color forth that is not a color forth, really, that is more user friendly. Okay, I think that's it for this one. If you want me to carry on, I have various other things I can show, but maybe it's best if I let Atli have a go.
All right, thank you. So, I don't know. I think Don is about to talk. Ashley already. I mean, Dimitri did.
Dimitri,
Ashley
okay.
is next.
If there's time, I can do a short thing about what I'm doing with Forth as well. If there's time.
Yeah, Peter, what do you think?
Yes, yes. You
maybe?
can be Ulrich, be free as you wish. We have Howard, Don, and we have Atle with the problem with the microphone. So I don't know if.
Oh, I see. I see. Anthony has a question, so maybe we do that.
Just to Howard,
yeah.
I was in similar positions of presenting text in colors, and I went to the standard VT100 code, which uses escape codes. And you are absolutely right that it takes 2 or sometimes 3-fold of characters you have to send over. But today's computers work reliable on 230 kilobytes. And that compensates for the additional characters.
Yeah. I'm actually operating at 9,600, what's it, 961,200 or whatever, the highest my hardware will go at.
Okay.
And that's really fast. So yeah, there is you have a point that there's no real need to compact things. So I'm not making any attempt to. If I was to do that, I would send a color change code first, and then say, I've changed to blue, then everything else is blue until I change it again, and that would compact it. What I'm aiming for here is I'm trying to think in terms of 32 bits always. So it's really a kind of a playground for me to try out ideas of what does it look like, and it's surprisingly hard. I think I made a mistake trying to use Windows to draw the full set of Unicode characters, or 16-bit Unicode, because I tried for hours. I cannot find out the width of the text string that it has drawn. So I think I'm going to change that. And I did it as the easy option, but it's proved not to be easy. So what I'm going to do, I think, is capture all the fonts that I need, maybe from Windows, but you didn't hear it here, and then put that in as a font, and then use that, because I'm actually using 48 pixel by some high number. What would be 36 by 48 or 24 by 48 pixels, so very high res, and then I'm scaling it down with the Windows scaled Windows features. Oh, it's complicated, but it means that the thing looks nice. If I go back to it, oh, you probably can't see it now. But so I can. Okay, it looked like it was going to be easier to do it that way, but because I'm now tied into Windows, if Windows is not working properly or the way I expect it or the way it's documented, then I'm stuck. So I think I might go back to a simpler thing. Okay. Yeah, sure. Don, I have to go away anyway quite soon. But whether I'll be allowed back, I don't know. But yeah, far away.
Don, please.
Okay. Well, I wanted to thank Dimitri he's really inspired me to work on this FPGA version. As you know, back in the late 90s, I wrote one in VHDL, and it wasn't really, probably wasn't a synthesizable one. I was trying to write a fourth processor in what's called behavioral HDL, which means a very high level. And I threw out my raw source code and said, if anyone wants to take a crack at converting it to System Verilog, which is what my new HDL language is, and I believe that there's some benefits to System Verilog, you know, if you want to take a crack at it, you know, here's the code. And a month later, Dimitri says, here it is. So he's got me going down this, designing my first fourth processor in System Verilog, which is very high level HDL. The code that I will show you today I haven't tested it. And so I'm not guaranteeing that it's going to work, but you're going to see where we're going with this. So the idea here is to have a fourth engine written in a language, System Verilog, which is very C-like. Almost everybody knows C. So you're going to know System Verilog. It's the same syntax as C. So almost everyone here would be able to extend the System Verilog code. And so we want to make it very high level. We don't care that it's the fastest chip on the planet. Dr. Ting's or the J1 or you know, some of these other ones. Ilya's is written in what's called register transfer logic, which is very low level. They're bit banging things and they're building the engine from scratch. So we're not doing that. We're doing this from a very high level. So I kind of coined a term. This is CISC. You know, it's a complex, you know, instruction set for a computer on RISC engine. So RISC being the fourth. So I'm calling it Core 1. So the idea is this: supercomputer on a chip. It's a fourth FPGA computer. You could have many instances. You could have maybe hundreds of these things instantiated on the chip. My goal was to develop AI systems, and I had talked to Dimitri about that. And we had discussions on Lisp and Prolog and that sort of thing. And I said, you know, boy, it would really be cool to be able to, you know, implement one of these AI languages right inside the chip. And then he went off and I told him that there was, I remember a book on, you know, fourth and, or Prolog written in fourth, and he went out and found it, and there he goes again. He just started coding. He's a tremendous coder. So here's the architecture of the system. So the idea here is you would have an external, let's just say we have an LVDS LCD panel that plugs in. We have something written in System Verilog that runs the display of a keyboard. We have the main 32-bit fourth computer. And I'm saying computer because it has both RAM and ROM inside of it. So it is truly a computer, not just a microprocessor. You can strip it down and actually have microprocessors that doesn't have, you know, you don't have to, you know, you can run without RAM and ROM in it. So you might want to strip those down, and you could have these as high-level processors inside of the FPGA. So here's one on the same network. So this is very much like the green arrays style. So here's, you know, we have all these fourth computers are 32-bit. I ran this by Dr. Ting. I had originally had a 16-bit. He says, why don't you make it 32 bits? I said, great idea. And so these are all 32-bit engines. Here's an example of kind of the GA144 style, when you have basically a network of fourth engines coming out. And then you always have, you can have FPGA fabric. So this FPGA fabric means that you can write custom processes, and an FPGA is like a little tiny microcontroller that just does, maybe it's running a sonar, or it's running a servo motor or something like that. So System Verilog is going to be the assembler of this computer. So here's an example of, this is another one. This is directly bolted onto the fourth computer. So the fourth computer, what you notice is it can have different interfaces. So you can have parallel interfaces to these other fourth processors, right? So you can put them in series, you can put them on the same network and bolt them to the fourth computer to do different things. So this is a multi-processor system. So these are our goals for the system. Very high level System Verilog code, which is easy to read and understand. Let the synthesizer build the circuit. You know, don't build it, you know, bit by bit, you know, using RTL. Most FPGA force our code with RTL. Like I said, register transfer logic. Define a stripped down version for multi-processor applications. Design a complete computer, including fabric, RAM and ROM, plus internal, that is internal memory. Code code that you want to run super fast, think assembler, you write in System Verilog and you make it a word. You add a new word to the system. Code in high-level sequential processing, you write in fourth words. So, for example, this is going to be a token-based system. Like Ulrich actually has a great paper on writing a tokenized inter-interpreter for fourth, which I'm going to be really reading that paper quite thoroughly when we get into writing the inter-interpreter. But you could, let's say we take Dimitri's fourth code where he's written Prolog, and you could literally take that code and put it in ROM, and when the system boots up, it will already have the code that implements Prolog inside of the chip. So we could implement other high-level languages, maybe a neural network language, and other types of things we can extend. I've been talking on many talks about extending forth instead of just the primitive words that it knows, things like arrays, for example. We'd have array words built right into it. We have AI type words. We have motor control words built right into this system, and it'd be on a single chip. So this is kind of an example of an idea where, you know, basically you have this fourth engine, and you can literally make, you know, like we tie an LCD to it, then we're making a tablet, a fourth supercomputer tablet. The Wi-Fi Bluetooth ADC stuff would be on an ESP32, since, you know, that costs $3-4 bucks. But you'd have interfaces for keyboard and mouse. Now, I've done this before in a previous job. What I did was they asked me to, they wanted to take an FPGA and they wanted to have a small LCD screen. Their screen was like 320 by 256, I think it was. It was a SPA controller. And they said they wanted to control the screen, including graphics. So what I did was, and they wanted it on an FPGA. So I put SRAM in the middle. See this SRAM? So the SRAM is actually the frame buffer for the LCD. And we now have dual ported SRAM, so you could read and write at the same time. And I found a 1 meg by 36 SRAM that'd be perfect for this application. So if you want to put something on the screen, you just load those pixels. You know, each cell, each 32-bit cell is a pixel with the 3 colors in it, and it just outputs to the LCD. So let's say you wanted to copy a screen, you could copy it in a 60th of a second, because this is all going to be written in System Verilog, and it's going to be running at real time. So if you want to copy an image on the screen, you want to copy it into SRAM, which is down on the right there, that NV SRAM. This system could copy that image in a 60th of a second. One, you know, what it takes to paint the entire screen. The non-volatile SRAM. So this is new technology. I think it's called an FRAM. And when you turn the computer off, it remembers everything. So if you changed if you updated your forth code, and maybe you have, you know, it just instant on. You turn it off and turn it on again, and you're exactly where you're at. You don't have to save everything to disk and then reload it. You know how Windows does it. And also it'd have an SD card, and that's basically your hard drive. So let's take a look at RISC-V versus FPGA. So at work, we're using RISC-V inside of an FPGA for a space application. And this is literally what we've done. So you notice that there's an AHB bus. You see the arrow, see right here, this bus right here. So all of these things you have to share. This RISC-V has to, you know, this is all memory maps. So the RISC-V has to change the address, and then it has to wait for one of these things to respond. And obviously only one of these things can respond at a time. So you'd have to use, if you wanted real-time control, you'd have to add like an interrupt line coming back to the RISC, for example. But we're doing things in parallel. This is a parallel machine. So there's no interrupt. You don't need any interrupts with this style machine. So this would be a very basic, this is what we're building right now. I'm not working on the display and the serial controller, but basically these three, you got the boot ROM, the internal RAM, and the fourth computer. That's what we're working on. And if you want to extend it, because inside an FPGA, you could have RAM and ROM. And then you can put these on the outside. Then you have to obviously put data bus and address bus and the interface logic if you want to use external. I've given talks about my Trine OS architecture, and we're going to be using that. And as Dimitri said, we would be using things like Prolog at the goal level of the TOS architecture to do the path planning. And then the instinct and behavior level stuff will be implemented in Fabric, or it can also be implemented at a higher level. So being able to add something like Prolog into a chip, you know, a single chip that's running 4